Hi, my name is Nafi Ahmed. I'm a PhD researcher at Queen Mary University of London's Network Group. Today I'm presenting a work on how different levels of packet loss ratios affect the quality of experience or QoE for passive video game streaming services. It is known that different quality of service parameters like latency, packet loss, jitter does affect the QoE of end user for various applications. Many researches have been carried out on QoS to QoE mapping for video streaming, but they're generally focused on traditional video on demand and video streaming applications such as YouTube and Netflix. We focused on a new emerging platform, that is video game streaming. Over the past few years, online game streaming has become increasingly popular with the introduction of Twitch and YouTube Live. But few works have been done on gaming videos which uses artificial generation of objects and therefore would require a more comprehensive study. Moreover, most studies on subjective QoS to QoE mapping uses mean opinion score or MOS method, but it is known that it loses information about user diversity. Standard deviation of opinion score or SOS is also used in conjunction with MOS, but we have found in our work that even that is not enough in some cases. So we came up with a novel method of presenting combination of MOS, SOS and user rating distribution to give comprehensive way of assessing QoE. Finally, we also observed how speed and content complexity of games can affect the perceived QoE. We selected 3 different games based on pace, content and popularity. They are Battlefield 5, League of Legends and FIFA 20. To understand the complexity of the video content, spatial and temporal information were calculated and shown in Figure 2. We can see that FIFA 20 had least SI and TI compared to other games because it is a slow-paced game with adjacent frames having similar layout. On the other hand, Battlefield had most SI and TI with its fast-paced action and the point of view being its first person. We used subjective testing to evaluate the QoE of 15 different videos at different PLR. It was a double-blind test where after watching each video the user ranked them on a 5-scale absolute category rating ACR that was later translated to MOS. These MOS values were mapped onto PLR using regression analysis which yielded an exponential function. MOS, SOS and user rating distribution were together plotted as shown in Figure 3. Our results shows MOS loses information about user diversity. For example, at low PLR, MOS was 4 or higher for all 3 games, but the distribution showed that there were users who perceived the quality to be lower than 4 for all 3 games. Similar examples are seen when PLR values are larger. Analysis of SOS shows that a difference of 1 or 2 user rating at a certain network scenario results in non-trivial SOS values as seen for FIFA 20 at PLR 0.8%. This poses a challenge to quantitatively relate SOS with user diversity in scenarios where there are more variations in rating. So a combination of QoE metrics of MOS, SOS and distribution retains most information about user rating and its diversity as shown in Figure 3. Moreover, all 3 games are affected differently by PLR. Slower games like FIFA were affected more by network degradation. Fast-paced games like Battlefield showed more variation in user ratings. In conclusion, we presented a comparative study of using different metrics like MOS, SOS and user rating distributions to evaluate the QoE of passive gaming video streaming. We demonstrated limitations of QoE evaluations using MOS by showing it loses information regarding user diversity. We presented our subjective QoE results as distributions and showed that it retains user diversity and provided a comprehensive way of assessing QoE. We also found that increasing levels of PLR affect the video quality of the slow-paced game with low temporal information more than the games like Battlefield. Hopefully this presentation gave a basic idea of our paper, and thank you for listening.
Hello, I'm Stefan Fremerey from TU Ilmenau and I will present you my poster, Development and Evaluation of a Test Setup to Investigate Distance Differences in Immersive Virtual Environments today. So nowadays a lot of immersive virtual environments is developed. What's usual in these environments that you always have some kind of tracking, for example the HTC Vive Lighthouse tracking, and this could lead to offsets between the real and the virtual environment. What I mean, if you have a real object and this is tracked, and you have a virtual exact replication of this object, and these two objects are not exactly at the same place, this could really lead to problems when trying to interact with these objects. Little research has been done on this field. So we asked us two questions. So what is the offset value from which the perceived grade of confusion is increasing, and whether there's any influence of the offset level on the task completion time and the performance, and whether there's any learning effect. For doing this, we developed a test framework using Unity 3D. So how we did this, we had our real test room here, and we generated a virtual test room according to this real test room. And then we conducted a subjective test with 18 participants. They had to fulfill a relatively simple pick and place task. So their task was that they had this cylinder here, which was tracked by a HTC Vive tracker, and they had to put it into this other open cylinder. And the position of this open cylinder was moved at certain offset levels, as it is written here. And they had the task, please place the cylinder inside the other open cylinder as fast as possible. So between these trials, the translational directions of the offset levels was randomized, so these directions here, but the order of the offsets itself not. And after the task completion, subjects had to rate their personal grade of confusion using the ACR scale, and before and every after test they had to fill in a short simulator sickness questionnaire values. In general, we reported no problems with the IVE per se in terms of simulator sickness because there were really low values of dizziness, headache, and eye strain. Also, every subject was able to fulfill this task at every offset level. What we can see, and we have a pretty low amount of confusion for the condition with no offset. But if you go to higher ones, then so for 1 centimeter, it's also still fine. But if you go to higher ones, for example, starting from 2 centimeters, we really get higher confusion, higher mean grades of confusion, and also the task completion time is really rising. For an offset of 3 centimeter, the grade of confusion is also again a little bit higher than for the 2 centimeter condition, but it's still fine, let's say. Even though the task completion time is even slightly decreasing for 3 and 4 centimeters, and this could be related to a learning effect of the subjects, which is slightly or relatively slowly evolving over time, which you can see here. And we even have an increase of the confusion, even though the order of the offsets is not randomized. So this increase is meant. In general, we can say that we have developed a publicly available test framework. You can also scan the QR code and get some further information on this. And this IVE can in principle be utilized to measure these effects of these distance differences. And starting from a 2 centimeter offset, the grade of confusion and the task completion time is extremely increasing. And also the results are important for researchers and designers creating some IVEs. They should pay attention that these offsets are really equal to or below 1 centimeter. In our future work, we plan to integrate more subjects into the tests, then some gradations also between the offset values, randomize the order of the offsets, and also implement some hand and arm tracking. Thank you for your attention, and I would be happy to answer further questions in the question round later. Thank you.
Hello and welcome to the presentation of our research results. This presentation is part of the 12th International Conference on Quality of Multimedia Experience 2020. My name is Jan-Niklas Vogt-Antons, and I'm a researcher at the Quality and Usability Lab of Technische Universität Berlin. During the next 4 minutes, I will present the aim, research method, and result of our work with the title Influence of Hand Tracking as a Way of Interaction in Virtual Reality on User Experience. This work was performed together with my colleagues Tanja Kojic, Danish Ali, and Sebastian Möller. Motivating this work was the fact that we were interested in getting to know how user would experience the new built-in hand tracking feature of the Oculus Quest and how different task types and visualization would change this experience. How was the study design? We used the Oculus Quest. Had 2 different application tasks, one with a grabbing task and one with a typing task, and in total 4 different ways of how this interaction could be performed and visualized. On the one hand, having the controller visualized with hands together. Second would be having the visualized controller but no hands in the visualization, pure controller. The third one would be having the hands visualized but no visualization of the controllers. And the fourth would be having the visualized hands while using the hand tracking. So the first three with controller, the last one with hand tracking. It was within participant design. We had different scales, like the self-assessment mannequin for emotional response, the presence questionnaire to learn something about the experience presence and realism of the scene, and the system usability scale to learn something about the usability of the system. In total, we tested 20 participants. This resulted in that results. Here we see the comparison of the different task types, so the grabbing task and the typing task. We see the mean values for the arousal scale, the presence scale, and the realness scale for the two task types. And what we can see here that for the typing task we have a higher arousal, we have a slightly lower presence rating, and a lower realism rating. We split the results for comparing for this four different visualizations. We can quite nicely see that we have a lower arousal rating for the hand tracking compared to all other interaction techniques with the controller. We have a lower dominance value in comparison to all those, and a higher valence rating. So to sum that up, it seems that a grabbing task is more natural, so we have a higher realism and a higher presence rating of participants. The typing task, in contrast, seems to be higher demanding, so it's more unnatural and therefore resulting in a higher arousal. Comparing the different visualizations and interaction types, we could show that the hand tracking is experienced as being less arousing, more positive in terms of higher valence, and less dominant. If you have any questions or comments, please contact me. Thank you very much.
Hello, my name is Waqar Salai and currently I am a PhD student in University of Nantes, France. Today I am presenting a paper poster accepted in QoMEX 2020. So the title of my paper is Can Visual Scan Pass Reveal Personal Image Memorability in Investigation of HMM Tool for Case Pattern Analysis. In this paper we study eye pattern changes for image memorability and propose a novel approach for classifying scan pass based on hidden Markov model. Image memorability is a new field of research in computer science. It is defined as the probability of an image to be recognized a few minutes after a single view. The dataset we used was recorded in University of Nantes. It is a 3-session experiment. In this study, only the first session on short-term image memorability was used. Short-term memorability was measured after a few minutes of a memorization process. A sequence of 200 images were presented to the observer, out of which 50 were repeated twice. An observer had to recognize them by pressing a button. If the image has already seen before, the observer response for each target image are then clustered into two classes, correct or wrong recognition. The eye data was recorded using a SMI red eye tracker of 50 Hz. Observing the facts that the eye pattern for correct and wrong responses in encoding phase seem similar to pattern in a recognition phase, whereas they seem different for each other. We assume that the visual behavior could be used to predict the observer memorability of the image. Towards that, we first use HMM algorithm to model a scan path for each observation. HMM is a probabilistic method which has been processed and trusting to model eye data as a time series data. The model of a choke was used, which consists in the definition of HMM state as a case point cluster. For each content, the individual HMM of each of the observations were then clustered into joint HMM for correct and wrong cluster with the variation hierarchical expectation maximization algorithm. From this method, we have for each content 4 different joint HMM, one for correct and wrong cluster for the encoding and recognition phases. We propose then two types of analysis to compute this model in order to predict personal image memorability. In first analysis, scan paths are clustered into correct and wrong classes for each phase separately. The class of the given scan path is determined with the usage of Viterbi decoder algorithm. We use the leave one out cross validation in our experiment. The proposed schemes achieve 44% and 58% mean accuracy for the encoding and revision data separately. In the second analysis, scan paths are analyzed across the phases. The joint HMM are determined with the encoding phase data and the class is predicted with the recognition phase scan path. So these proposed method achieves 61% accuracy. We also computed the t-test between the likelihood vector. Statistical result shows 20 significant different pairs between vector LCC and LCW comparison with the correct encoding scan path, and 5 significant different pair for vector LWC and LWW comparison with the wrong encoding scan path. In the conclusion, results show significant difference eye pattern for correct and wrong responses, and the proposed scenario for image prediction based on case data give promising result for the use of interact mirrors in a personalized quality of experience assessment. However, these results merits to be further investigated to improve the performance and construct more concrete scenario. Thank you.
Hello, my name is Carlos Cortés. I'm a PhD student from the Image Processing Group of the Polytechnical University of Madrid. I'm here to present my poster, Influence of Video Delay on Quality, Presence and Sickness in Viewport Adaptive Immersive Streaming. Extended reality applications usually use omnidirectional video to improve users' immersion. The end-to-end delay becomes a key problem when the user's reaction cannot be simultaneously matched by the system's reaction. Thus, an experiment to assess delay influence on the quality experience has been designed and carried out. A viewport adaptive simulator was designed under the Unity 3D engine. This simulator consists in two different spheres, which draw two different kinds of video frames. The nearest sphere shows only a portion of its area according to the user's field of view. However, the farther sphere is fully visible. The field of view portion will follow the user's movement using different delay values. This configuration makes possible to simulate different adaptive streaming situations that are listed below. The schemes presented are a different combination of PTC cameras. The effects of the nearest sphere delayed movement can be watched in the three images below. The head-mounted display Lenovo Mirage Solo was used in the experiment as play device. Both delay groups included 0 milliseconds as hidden reference. 20 participants with ages between 22 and 40 watched 9 clips of 20 seconds from 3 different sources. Quality, presence, and distance were used to assess quality of experience. Users always start watching the video in the highest quality. Degradation category rating was used to measure video quality. To measure presence, the Multimedia test was used. Also, to measure dizziness, two different questionnaires were used at different stages of the experiment. On the one hand, the simulator presented a question about sickness at the end of each sequence. On the other hand, before starting the experiment and each part of the session, the simulator sickness questionnaire was filled by the users to analyze the temporal evolution of the cyber sickness. Video quality results show that there is a strong dependency between delay and video quality, also that the PTC scheme is significantly worse than the rest of the schemes. The results of presence and sickness show that there is no significant difference between adaptation schemes or delay groups. The results of the video quality show that the PTC video delivery scheme is significantly worse than PTC over pre-recorded background scheme, foveated imaging, and tilt-based schemes. Also, adding 360 information to a PTC adaptive schemes enhance the perceived quality of experience. Regarding sense of presence and simulator sickness, the results show that there level of delay, not the selection of a specific adaptation scheme, have a significant influence on the perceived quality of experience. This supports the possibility of using PTZ cameras within virtual reality setups. Furthermore, further research can extend this result using higher quality videos or lower delays.
Hello, this is Babak Nader, Technical University of Berlin, presenting our paper Transformation of Mean Opinion Scores to Avoid Misleading of Rank-Based Statistical Techniques. The rank-based statistical techniques consider two items make a tied rank when they have an equal numeric value. Otherwise, they will get two different ranks despite how small the numeric difference was. This definition is not suitable for mean opinion scores, as we will show how two equal most values are rarely observed in subjective tests, even in test-retest studies. We introduce a transformation method to apply on most values before using any rank-based statistical technique. The method checks when two most values should be considered equal using their 95% confidence interval and assign the same rank to them. We provide an open source implementation of method in different software packages to ease its usage. The mean opinion score present on average over the opinion score given on predefined scales in the subjective test. Typically, a 5-point discrete scale is used. The resulting most value is very sensitive to changes of participants' rating. In the example, 9 out of 10 participants provide exactly the same ratings, and only the last one gave a rating with 1 point deviation in ACR scale. It leads to 0.1 difference in most value between two stimuli. Similarly, difference of 0.01 most value can be observed when 99% of participants provide exactly the same rating and 1% gave a rating with 1 point deviation in ACR scale. Now the question is that if they should be considered to be equal or different. Now, what will happen if a tied rank is missed? A numeric example is provided here. Vector B has two most values which are very close together, namely for S2 and S5, and vector C, vector B prime has the same values, only S2 and S5 has equal numbers. You can see that it leads to a considerable difference in the spearmint rank correlation coefficients. We also provide a formula to calculate maximum effect that missing M-tied rank can have. In the plot, you can see that the number is tangible when the amount of condition in the study are below 15. So how often very close values may be observed? We examine 18 datasets from this domain of speech quality assessment. In the graph, the blue line shows the difference in the most values of the two consecutive items in the rank order, and the red plot shows the distribution of a 95% confidence interval. In 86% of times, the difference was smaller than the 95% confidence interval of the most values. Now we use these rules for transforming the most values. In case a most value is in the 95% confidence interval range of the other one, then they can join together to make a tied rank, like plot C. Another most value can join to the existing set of tied rank only if it is make a tied rank with all elements in that set. So it is not the case neither in plot D or E. For other details, please read the other rules. Finally, we conducted a simulation study to see effect of using our transformation methods. We took 10 degradation conditions from a lab test and added randomly generated white noise to them. Then we calculated the Spearman rank correlation between truemost and the noisymost values with and without our transformation method. The plot illustrates the largest observed difference in 1,000 simulation runs. And here is a link to open source implementation of our transformation method for MATLAB, Python, and R. Thank you very much.
Welcome to the poster presentation towards analyzing the interaction between quality and storytelling for event video recording. I am Eckhard Stoll and the co-authors are Professors Breide and Rake. Video recordings of stage events are difficult to realize in a non-professional environment. Framing is often of poor quality. For example, heads are not always completely visible or the actors are misplaced in the frame. High-resolution cameras can help. Only long shots or medium long shots are recorded. Medium shots and close-ups are obtained later in post-production. Our study investigated how test persons evaluate the use of different image sections and resolutions in a real scene. A 30-minute scene of the theater recording was created in 3 different versions with different image sections. One camera was fixed in the middle for taking long shots. The other 3 cameras were placed on the right, left and center and recorded medium long shots. The scene consists of 32 shots. Here we see the first 4 shots in the 3 different versions. For version 1, the full resolution without cropping was used. For version 2, medium close shots were applied with mainly 2 persons shown. Version 3 comprises a larger number of shots with more individual close-up faces. Here we see the horizontal resolution of the shots in relation to a playing time. Version 1 has 3880 pixels throughout. In version 2, the range is between about 1000 pixels and full resolution. In version 3, we have resolutions down to about 800 pixels. In an online study, the 3 versions were to be evaluated, all scaled to full high definition. The test persons could use their smartphone, tablet, notebook, PC or television. The entire questionnaire was designed on a single website to watch the 3 films several times and also in any order to compare the ratings. The liking and the image quality were to be evaluated on a scale from 0 to 10. Image width, image height, and viewing distance also had to be specified. 72 respondents took part in the study. Version 2 was chosen by almost half of the test persons and received the highest liking scores. Version 1 received more votes than version 3. Although the shots in version 2 are almost created by downscaling and not by upscaling, the quality is rated about 1 scale point lower. Version 3 was rated about 2 scale points lower than version 1. Surprisingly, version 3 was more often preferred when viewed on a PC than on a notebook or smartphone. We expected the opposite, because smartphone screens are much smaller and viewers are often assumed to prefer close shots here. To examine this in more detail, we looked at each preference in relation to a relative viewing distance. We see that the respondent smartphones yield smaller viewing angles than notebooks or PCs. Here, upscaling, as increasingly used in version 3, would be less noticeable than with larger viewing angles. Nevertheless, smartphone users have not so often chosen version 3 as their preference. In this case, smartphone users gave us reasons that they liked the overview of the events in versions 1 and 2 better, or that the perspectives provided a balanced mixture between the whole scene and portraits. In summary, the study found that viewers tolerate a loss of quality and prefer a version that is closer to a stage action in terms of content, even if the image quality is rated worse. Due to further development of cameras with increasing resolution, it can be assumed that the production process will be able to achieve better quality in the future, as close shots can be cropped with better resolution. Thank you for listening.
Good morning, good evening, or good night. My name is Jason Quinlan, and I'm one of the authors of GoDash, a Go-accelerated HAS framework for rapid prototyping. So the goal of this work was to create a Dash or HAS video player, headless, which means it doesn't decode the segments that it downloads, but written in Golang, an open source programming language supported by Google, also known as Google Go. So we wanted to be able to have a low memory, easily modifiable and configurable player written in Google Go. What was most important to us initially was to also be able to have 2 transportation protocols, namely TCP and QuIC. Okay, so QuIC, if you don't know, is a new protocol, again, which uses UDP rather than TCP as the underlying transmission protocol. Okay, so enable my little laser pointer. So some of the options that we have implemented in the initial version or the initial release of Go Dash is we have some existing algorithms added. So we've got hybrid algorithms such as Arbiter Plus and Elastic, buffer-based, logistic and BBA, and rate-based, which is conventional, average, progressive, geometric, and exponential. We support 4 different video codecs: H.264, H.265, VP9, and AV1. Again, these are all just for downloading, so we can download these codecs, but we don't decode these codecs. We've also implemented support for 5 of the 6 dash profiles, so full, main, live, full byte range, and main byte range. The only one that we haven't implemented is on demand, because with on demand you need to decode the segments to extract information for on the underlying video. We have an option for requesting all the header information on the segment, so to determine what's the byte size or the transmission cost of each segment, you request all the header information, and some of the algorithms need those kind of stuff. So we, as I said, TCP and Quick, we have configuration, which is a sample up here, working configuration file. We can determine the maximum segments to buffer. We have initial segments to download, startup phase, maximum height, and Go Dash comes with its own testbed framework, which we call Go-Bed. Framework uses Mininet to serve content locally, and we also have implemented VoIP background clients for a little bit of background traffic. Okay, configuration 5 is relatively simple. You call with the parameter dash config, you pass it a configuration file. So here you can see we've set as the adaptation algorithm is conventional. We're using H.264. We want to have debug logs. We're going to say the initial 2 segments. We're going to buffer before we start to play. The maximum buffer for this player is 60 seconds. We're going to have a maximum resolution of, that's 4K realistically, stream duration of 4 seconds realistically here. We're going to store our output logs in this file. This is the file structure for those output logs. We're not going to get headers, we don't need them. We're going to output our content straight to terminal print so we can see what's being printed to terminal. These are the headers that we're going to request. So these are headers that we have down here in our output logs. So you can see set some of them to on and off. So the initial ones here are all by default, whereas these additional ones, you can select them to be on or off depending on what kind of information you want saved in your logs. Here you can see we're with HLS, that's only experimental for the moment. X ratio is used by one of the algorithms. Quick is on or off. There's the URL that you're going to download your content from and use our testbed. So at the moment, Quick only works within the testbed. So if you're going to use the testbed, testbed will be on and Quick will be on. Quick off will use TCP, Quick on will use Quick. As you see down here, these are some of the outputs that we have then as well. So we can have, these are default and will always be there, mandated by default, and these are options. So you can switch them on or off in the config file. We get some information on here where we show a number of output segments. Okay, so it's arrival time, delivery time, running all the way through to the codec choosing the width, the height, frames per second, and the underlying transmission protocol. Okay, so that's a very, very quick overview of Go Dash, and I've gone over my 4 minutes. Instructions on building it is down here. My email is over here. If you want to get in touch, send me a mail. Talk to you soon. Enjoy the conference.
Hello, my name is Owen Hines. I'm a PhD candidate in the Department of Electronics and Informatics in the Athlone Institute of Technology under the supervision of Dr. Ronan Flynn, Dr. Niall Murray and Dr. Brian Lee. The title of my paper is a QoE evaluation of an augmented reality procedure assistance application. Augmented reality is a key technology to enhance worker effectiveness during increasing automation and mass customization in Industry 4.0. User quality of experience will inform acceptability of AR for this role. Acceptability of AR for these roles will result from a quality judgment made by the AR user based upon post-experience reflection of their degree of delight or annoyance relating to how well the AR application fulfilled their pragmatic and hedonic needs and expectations. Delight and annoyance are used as emotional labels throughout the literature. The literature also shows that emotion is expressed in the frequency of head rotation around pitch, yaw and roll axes. Specifically, that high frequency head rotation expresses anger emotion exclusively. The focus of this work is in using the frequency of head rotation around these 3 axes to infer the user's degree of delight or annoyance. The experimental methodology used an optimal Rubik's Cube solving procedure. In the AR test group, the test subjects were provided with the instructions using the Meta 2 AR head-mounted display as seen in this picture here. The AR application was compared against a paper-based instructional manual control medium. The methodology consisted of information, screening, training, practice, testing, and questionnaire phases. During the task, a Logitech 1080p video camera used in conjunction with OpenFace was used to estimate the test subject's head rotation around pitch, yaw, and roll axes. For the purposes of this demo paper, an 8-second post-task sample of head rotation was used to evaluate the amount of expression of anger emotion. The time domain OpenFace output was passed through a Fourier transform in MATLAB to obtain the frequencies and amplitudes of the test subject's head rotations. Results showed that AR yielded successful task completion in 96% of cases, where the control medium resulted in 92% successful task completion. There was a significant difference in task duration between the groups in favor of augmented reality. Meanwhile, the control group expressed significantly higher amplitudes of the high-frequency anger head rotations than the AR group on all 3 axes of rotation. Figure 3 shows the minimum, mean, and maximum amplitudes of the high-frequency head rotations for both groups. We see that the AR group's combined amplitudes for yaw, pitch, and roll are consistent across the high range of frequencies at about 0.04 radians, while the control group's mean, yaw, pitch, and roll amplitudes are about twice that. Figure 4 shows each individual test subject's mean, yaw, pitch, and roll amplitudes of the high range frequencies plotted against their task completion times, and we can see that there is a minor effect between increasing task durations and higher amplitudes of the high frequency head rotations. In conclusion, while the AR yielded higher task success rates and significantly reduced task durations, the AR test subjects expressed significantly lower mean amplitudes of the high range anger frequencies of head rotation on all 3 axes. Longer task durations were seen to account for slightly higher amplitudes in the high frequency head rotations. By reducing task durations, AR may therefore result in reduced amplitudes of these high frequency anger head rotations. Future work aims to evaluate head rotation frequency continuously during AR usage. This work was funded by the AIT President's Seed Fund. Thank you.
Welcome to the presentation of this poster, which is called Match Quality Evaluation of Temporally Downsampled Videos with Non-Integer Factors. My name is Christian Herglotz, and this work was done with Kitara Masubu and Andre Kaup. First of all, I would like to draw your attention to the 2 videos at the bottom. The top video is sampled at 50 frames per second and the bottom video at 25 frames per second. Now, what is funny about this is that the video that you are watching right now, the streamed video, has got a frame rate of 30 frames per second. That means in order to allow you to see these 2 videos, some resampling has to be done. Now, of course, what is interesting is to know about the quality degradation introduced by this resampling. If we have a look at the literature, so we look at the state of the art, then what you would find is that people usually look at integer downsampling factors. What does that mean? It means, for example, we've got a high frame rate sequence of 4 Hz and a low frame rate sequence of 1 Hz, which is an integer downsampling factor of 4. That means for 4 frames in the original sequence, we've got a single frame at the downsampled sequence. Now, to evaluate these 2 sequences, we can do a technique which is simple frame padding. That means we copy the preceding frame, this dark blue frame, 3 times, 1, 2, 3, and then we've got the possibility to compare each frame of the original sequence with a padded frame of the downsampled sequence. We can evaluate the traditional full reference quality metrics and obtain an estimate for the visual quality. Now, this is of course not possible for the case that we have right here of a non-integer downsampling. And what we propose to do in this case is explained in the box at the bottom left right here. So assume, for example, we've got a high frame rate sequence of 3 Hz and a low frame rate sequence of 2 Hz. Then we propose to patch both of them, so to upsample both of them to the least common multiple frame rate, which is shown here, which in this case would be 6 Hz. We patch both sequences, so we again copy the frames, like this one is copied once, the bottom frame is copied 2 times, and then again we have temporally matching frames. So if this on the x-axis is the time, then we can see that these two virtual frames, you could call them, occur at the same timestamp, and we can again calculate a traditional full reference quality metric. The algorithm to do this is explained in detail in this top box that I will not go into detail now. I'm happy if you are curious about it and have a look at the poster and the paper. But the result is shown at the top right here. The result is called matched quality metric, and this matched is put in front of each of the traditional quality metrics like PSNR, SSIM, and VMAF. So we've got, for example, matched PSNR. And if we apply this to an exemplary sequence, which at the beginning could be 120 Hz, we would downsample it to 100 Hz or 60 Hz, then we can obtain these quality metrics in matched PSNR, for example, in decibels. And of course, a lower frame rate means that we have a lower quality. This can also be applied to compression. In this case, we would have a rate distortion curve which uses the matched VMAF score, and each of these lines represents a constant frame rate. Blue is the highest frame rate and the other ones are lower frame rates. And we can see that for lower qualities, apparently, it is better in terms of rate distortion to have a lower frame rate than the maximum frame rate. So this is the end of this presentation. Thanks for listening.
Hello everyone, I'm Said Chafi Sabet from SimlaMed and Quality and Usability Lab from QoMEX. I, together with my colleagues Stephen Schmidt, Samuel Tudakach, and Professor Grevels and Professor Muller, investigated the influence of gamer strategy on the delay sensitivity of clock games. The negative effect of delay on gaming quality experience are already discussed in many papers, but the amount of this effect depends strongly on the game content. For example, a slow-paced card game is not as sensitive to delay as a shooting game. If we want to have an optimal resource allocation or quality estimation, it is highly important to consider the impact of the game content. This paper tries to provide a better understanding of the influence of content on the delay. What we are looking for in this paper is the gamer strategy. We investigated what would happen for the delay sensitivity if a player executes the same task with different strategies. For example, some players are more aggressive and always want to rush into the enemy, but some want to just sit somewhere and wait for the enemy and ambush. To answer these questions, we conducted a subjective study using 15 intermediate gamers, including 5 female.
Hello everybody and welcome to day 3 of QoMEX 2020. I hope you all enjoyed the posters in the virtual hub. It's just a short organizational announcement to go through the important events of today. So coming up next at 12 UTC is the third and final keynote. We have Professor Stephen Brewster from the University of Glasgow. After Stephen's keynote, we will be having our standard social Zoom at 1300 UTC, so please join me in Zoom for another social session. At 13:30, we'll be moving to our YouTube Live oral sessions, and today's sessions are exciting mix of video quality and novel QoE methods. At 1500 UTC, Ronan Flynn will be the chair of the final virtual hub lobby sessions, and Ronan will introduce the lobbies via the YouTube live stream. He'll then invite participants to join the virtual lobbies in the hub, and as with yesterday, there will be 2 pitch sessions going on in parallel in the hub. You can choose which pitch session to view. As with previous sessions, the virtual lobbies will be managed through the QoMEX Live link at the top of the website. Go to day 3 and scroll down to 1500, where you will see the links to the 2 pitch sessions. Underneath each of these, you have the papers with the names of the papers, which link directly to the papers, the VR goggles, which link you straight into the room of the particular paper presenter, and the red camera, which shows you the video offline. And at 16:30 UTC, we'll be having our awards ceremony, where we will present the best paper and best student paper awards, and we'll also have a short closing ceremony where we will introduce the QoMEX 2021 event. So, despite the online nature of QoMEX this year, there's been good participant interaction on both Slido asking questions during the keynotes and the oral sessions, and via the social channel on Slack, where discussions and conversations on the events happening on the live stream are taking place. So don't forget to interact via Slack, via Slido, and to tweet at QoMEX 2020 using the hashtag QoMEX 2020. Please stay tuned into YouTube Live here, and Stephen Brewster's keynote will be coming up soon. Thank you. Hello everybody and welcome to day 3 of QoMEX 2020. I hope you all enjoyed the posters in the virtual hub. It's just a short organizational announcement to go through the important events of today. So coming up next at 12 UTC is the third and final keynote. We have Professor Stephen Brewster from the University of Glasgow. After Stephen's keynote, we will be having our standard social Zoom at 1300 UTC, so please join me in Zoom for another social session. At 13:30, we'll be moving to our YouTube Live oral sessions, and today's sessions are an exciting mix of video quality and novel QoE methods. At 1500 UTC, Ronan Flynn will be the chair of the final virtual hub lobby sessions, and Ronan will introduce the lobbies via the YouTube live stream. He'll then invite participants to join the virtual lobbies in the hub, and as with yesterday, there will be 2 pitch sessions going on in parallel in the hub. You can choose which pitch session to view. As with previous sessions, the virtual lobbies will be managed through the QoMEX Live link at the top of the website. Go to day 3 and scroll down to 1500, where you will see the links to the 2 pitch sessions. Underneath each of these, you have the papers with the names of the papers, which link directly to the papers, the VR goggles, which link you straight into the room of the particular paper presenter, and the red camera, which shows you the video offline. And at 16:30 UTC, we'll be having our awards ceremony, where we will present the Best Paper and Best Student Paper awards, and we'll also have a short closing ceremony where we will introduce the QoMEX 2021 event. So, despite the online nature of QoMEX this year, there's been good participant interaction on both Slido asking questions during the keynotes and the oral sessions, and via the social channel on Slack, where discussions and conversations on the events happening on the live stream are taking place. So don't forget to interact via Slack, via Slido, and to tweet at QoMEX 2020 using the hashtag QoMEX 2020. Please stay tuned into YouTube Live here, and Stephen Brewster's keynote will be coming up soon. Thank you.
Hi everyone, my name is Stephen Brewster from the University of Glasgow, and I'm going to talk about how we're going to use sound for creating new multimedia experiences. So my research area is multimodal human-computer interaction. In this kind of area, we're interested in how people use all their senses and capabilities to interact with technology. Often when you interact with devices, you use quite a lot of your eyes and maybe a little bit of your fingers to touch things, but you don't really use all of the facilities you've got as a human, those rich senses, those rich control capabilities. So the area of multimodal interaction is about how we use those. So our aim is really to investigate what are the human capabilities, what are humans good at, and then design new interaction techniques and applications that take advantage of them. So we may use all the different senses, like touch, or vision, or hearing. We may use different control capabilities, like gesture or speech. And we look at how we can combine those to do new things in new kinds of ways. Audio, which is the kind of focus of my talk today. And I'm going to talk a bit more about our work on audio augmented reality. But we do lots of work on non-speech sounds, 3D audio, sonification, and things like that. I'll also talk a little bit about computer haptics, or how you might use your sense of touch for interaction. So we've done lots of work in the past on force feedback devices and pressure input and tactile displays, the kind of thing you might have on your phone. What I'll talk today about is ultrasound haptics, a new form of haptic feedback, and how you can also use that for levitation. We also use other things like physiological inputs, we call it affective displays, but they're not the focus of today's talk. So the application areas we apply our modalities in, well, we look a lot at touchscreen user interfaces, things you might use on mobile phones, for example, improving usability and the user experience there. We have a stream of work on in-car user interfaces and how you might create interesting user experiences in cars. Particular focus on VR and AR, so virtual reality and augmented reality. And I'll talk a little bit about some of our audio augmented reality work, but we're also doing work on visual virtual and augmented reality too. We do interaction with TV, which you'll see later on, and also things about accessibility and mental and physical health applications, which again I won't talk about today. So multimedia experiences, that's the focus of the conference and the thing that we're most interested in today. And here, sound is often a bit neglected. Visuals tend to dominate. And I think that's a shame, because sound has got a lot to offer. And this is not necessarily just sound for sound effects or speech. There's other kinds of interesting things that sound can do. And I'll give you some examples of those today, taken from 2 research projects that we've got going on right now. So the first one is using ultrasound, which is not a common technology used for interaction, but you can do some very interesting things with it. And I'll talk about how we might use it for haptics and levitation. And then I'll talk about some work on audio augmented reality and how we might create wearable audio environments that we can carry with us, and what we might be able to do with those if we can have such environments. So first up, ultrasound interaction. So if you remember back to your school days, if you have 2 sound sources close together, the sound waves coming out of those can interfere with each other, and they create patterns of high pressure and low pressure, as you can see in the picture at the bottom of the screen there. And you can use that to do interesting kind of things. For example, by combining enough of the speakers, you can create feelable forces. So you can have your hand in the air and you can create forces that you can feel. And you do that by clever combination of the timing from the loudspeakers. What do we use? Well, we use these. These are small ultrasound speakers, maybe that kind of size, and their main job is to be in your car bumpers so that when you reverse, you don't hit walls or back into things. So the technology in the speakers is nothing special, but what we do is we combine them in interesting ways and have very tight control over the amplitude and the phase or the timing of the speakers, which allows us to do some really interesting things, as you will see shortly. The video here shows what the sound field looks like. So here you can see the sound coming from an array of those speakers on the left hand side, and moving toward the right hand side you can see if we put something into the array there, into the sound field, you can see the sounds bouncing off it. And if that was your finger, you'd be able to feel the sounds, for example. You could feel those sound waves. So it's a little bit hard to kind of see that because the haptics is invisible. So here's another way of presenting it. Here you can see one of our arrays. You can see the speakers, the little black speakers I showed you in a square layout. And you can see that we can control these pieces of paper moving up and down by generating forces in the air. And if your finger was at one of those points, you'd be able to feel those forces. So what does that allow us to do? Well, it allows us some interesting kinds of things. So it allows a non-contact form of haptics. So if you think of a normal haptic device, maybe your mobile phone, normally you have to be in touch with that to feel the haptic forces. If you're not touching it, you can't feel it. The interesting thing about the ultrasound is we could beam it to your hand. So we can then fire the ultrasound forces at your hand or your fingers or wherever you like, so that we can generate forces to your hands without you having to hold or touch anything. So you can just have your hands in space and feel forces. We can also modulate those sound waves that I showed you in the videos previously to produce different textures and different roughnesses, so that you can create things that feel different. So you can create different shapes and you can create different textures. Interesting things that you might do with those. For example, we've been working on virtual controls. So here I might put my hand out and I can create something I can feel, and then I can press it. So maybe I create a big button which I can then press down with my hand. And I can create them where and when I need them. So maybe I don't need that button all the time, but if I do need it for an application, I can create it as and when it's needed. So here in my little picture, you can see I've created a slider. So maybe I'm working on some application, I need a slider. I can then reach out my hand, I can slide the slider and I can feel it. And when I'm done with it, it disappears. Or there's some buttons there I could press, or a dial I could turn. And when I don't need them anymore, they just disappear. So it allows me to create controls, touchable, feelable controls, where and when I want them, and then they can go away when I don't need them anymore. So it's a very kind of convenient way to expand your interaction space. So yeah, you might create virtual controls. You might have them on your PC to kind of increase the kind of workspace. You can imagine using these in VR and AR, so I can create haptic controls around me and feel them without having to hold controllers. We and others have looked at using them in car dashboards. So, for example, I may be driving and then reach out and feel a control, depending on which side of the road you're driving on, without having to reach over far to the center stack, for example. We'll also looked at using them on mobile phones. So there you might be able to create an interaction space around your phone or above your phone where I can interact in a larger space than touching on the screen itself. So it gives you a much larger interaction space, but actually you can use my sense of touch. So rather than just gesturing a space, I'm now using my sense of touch. So one other interesting, maybe even more interesting thing that you can do with ultrasound is then use it to levitate objects. So just as we can create those forces that you could feel, and I was moving those pieces of paper around to show that, you can feel them on your finger. What you can also do is use the levitation to hold small light objects in the air. So then we're creating physical pixels. So if you think about the digital pictures you might have on the screen that you're watching me on, well, we can create physical pixels that appear in space in front of you, levitated in the air. So this means that we can create these physical pixel-based displays and build them up into more complex displays made out of very many pixels. So we can then create complex 3D models that can appear in front of you and then disappear again when you don't need them. So maybe if I was designing a new mouse, I might be able to create a physical model of it made out of physical pixels, change it slightly. When I'm done with it, it disappears. So instead of having to 3D print a model, which might take some time, I can create one immediately in front of me and then it can go away again. So here's a simple early prototype from one of the partners on our levitation project. This is from the University of Sussex. So here you can see we're levitating multiple of these polystyrene beads. Polystyrene beads, they're nothing fancy. They're just the kind of polystyrene beads you might get in your packaging from Amazon or something like that. So you can see that we can levitate them into space. We can move the tweezers around to show that we're not holding them up with string or anything like that. So they're levitating there in space. And you can see at the bottom and the top of that setup there, small arrays of those loudspeakers I showed you right at the beginning. So here's a bigger array. This is a more up-to-date demo. So you can see one array at the bottom. There's also another one at the top. So it's sandwiched like this to create a strong sound field. And here you can see that we can now control the pixels quite precisely. So for example, marking the corners of a square or corners of a cube, which we can then rotate in space. Here's another version. So here we're rotating in a different dimension. Actually rotating this way is more complex than rotating horizontally as I showed you previously, because of the way you have to construct the sound field. So there's a lot of complex acoustics going on in the background here, but you can see, and you can see that so they kind of slightly wobble around a bit more than in the previous one. But these are pixels, hold it in the air, suspended in the air, and we can control and move them around very precisely. So of course we don't just want a display, we want an interaction too. This is supposed to be an interactive system. So here you can see with the cube that you saw before, now we can start to interact with it. So you can see Ewan in the background, using gestures to control the orientation and then the size of the square. Just in front of the display, between the display and Ewan's shirt, you can see a leap motion device, which is what we use to detect the hand position there. But you can see we've got very precise control of these pixels. We can put them where we want, and then we can move them around very precisely. As I mentioned before, this is all part of our levitation project. One other interesting thing you can do is you can integrate other objects into the scene. So here we've got bits of felt and bits of wire mesh. So the sound just passes through these, so they don't affect the sound field in any way. So that means we can then use these objects in the sound field. So now you can see that we can levitate our pixel, and then by dragging it, we can move it through these physical components. So it allows you to create displays which are made of physical components and levitating beads. So it gives us a kind of rich physical display where we control and move things around in a way that is not possible in any other kind of format. What might you do with it? Well, I hinted at these before. So for example, dynamic physical displays. So we can control the existence, form and appearance of these 3D objects. So we can create the different shapes, you can manipulate them and change them, then you can make them go away again when you don't need them. So for example, perhaps we want to create a shared visualization for something, we could create that, and then we could all walk around it and share it and look at it together, because it's a physical object sitting in space. It's not like using, say, a VR headset or something like that, where you're tricking your eyes into seeing 3D. This is a real 3D object that you've made in front of us, made of physical pixels. So you may do some kind of data physicalization, where you create a physical representation of your data and then move it around in real time. So this gives us new ways to understand data, new ways to understand information. So it's a kind of completely different way of representing our data. Now, of course, we're in the very early stages of this work. As you saw now, we're levitating a small number of beads rather than the millions that you might have on a large graphical display. So in many ways, we're as we were in the 1960s when we started creating simple visual pixel-based displays, and since then we've scaled them up to be multi-million pixel displays. So we're at the stage now where we can control the individual pixels, and the kind of further steps in this work are then to scale this up to a much larger scale, so that you can create much richer and larger objects, and that's what we're working on right now. So just to summarize this part of the talk, so ultrasound is not an area, or not a technology that's really been used in human-computer interaction at all. It's a completely novel modality, but there's some interesting things that you can do with it because of the properties of when you combine multiple ultrasound loudspeakers together and you carefully control the timing and the amplitude. So then you can create forces, either forces that you can feel on your hands or forces that can be used to support objects, or a mixture of both, of course. So this can provide some radical new ways for interacting with technology, creating new kinds of multimedia experiences, new ways of engaging your users. This nice idea of non-contact haptics. So I don't have to be holding anything. I could be reaching out into an environment and I could have haptics beamed to my hand where I need it. And then this idea of levitation of physical pixels. So now we can create physical objects. If I want my coffee cup, if I want a model of a coffee cup, I could make that in space in front of me as a model from these physical pixels. I can manipulate that, change it. Maybe I don't like the handle or something, change the handle, then the model goes away, and then I can send it to my 3D printer when I'm happy with it. So it gives us a whole new way of interacting with data and interacting with technology, allowing us to use the physical skills that humans have. If you remember at the beginning I was talking about multimodal interaction, we want to take advantage of those physical skills that users have, and this kind of display allows us to do that. So let's change gear and think about a different kind of use of audio. Rather than ultrasound, we're now going to think about audio augmented reality. So my group has been working in audio for a long time. I did my PhD in audio a very long time ago. And we thought a lot about non-speech sounds, things like ear cons, kind of sonic icons and how you design those, 3D sound and how you might use 3D sound for interaction. For example, progress bars. There's a little picture of a progress bar there. We had a sound that moved around your head. And we've done all sorts of things with 3D audio interactions. We've combined it with gestures so that you might point at things in 3D space. And we've investigated how you might use sound for interactive purposes. But a brand new project which we've just started has really been thinking how you might do audio augmented reality. So if you think about augmented reality as you commonly see it, this might be through a Microsoft HoloLens or a Magic Leap headset. The real idea is with one of those that I'm wearing this headset and I can create an object from the computer and present it in the visual environment, and I wouldn't be able to tell whether it was a real object or a virtual object. Now that's the end goal of augmented reality. I can put something into my visual environment and I couldn't tell whether it was real or virtual. Now that's currently extremely difficult to do. If you've used a HoloLens or a Magic Leap, they're really amazing, but you don't really believe that the graphical object that's been created is really part of the scene. The technology is not there to do that yet. But a really interesting thing is, in terms of audio augmented reality, we're much further forward. So adding convincing digital audio to the sound environment around us actually is a much more feasible thing to do. We now have technology to really help us do that. If you can see the pictures at the bottom of the slides here, these are some Bose frames which give you high quality audio. So you can see in the arms, they have loudspeakers in the arms facing in towards your ears. They have microphones as well. So they can generate very high quality audio for you as a listener. The idea here is that they're acoustically transparent. So they can take in sound from the real world because they don't cover your ears. The sounds just come in the ears as normal. But because they've got sounds in the frame, you can also add extra sounds rendered from a computer into the audio environment. So it creates this idea of acoustic transparency, this intermixing of real and virtual sound. So these Bose ones, you can buy them now, they're not too expensive. An interesting thing about them is they just look like normal sunglasses. So I've worn them walking down the street. You don't feel weird. If you wore a Microsoft HoloLens walking down the street, you'd probably feel weird. The nice thing about these is they're small, they're compact, and they can generate high quality sound. So we've been thinking about how you might use this. So you're now carrying an audio augmented reality environment around with you in the world. So how can you use that? What can you use it for? And we've also focused on what different kinds of audio you might present, and can we really trick the user into not knowing whether there's something which we're generating ourselves versus something that's coming from the environment. So there's a video here which gives you more detail. I'm not going to show all of it now. I'll just say the first part because it's kind of quite fun. This is us running around recording things around the university with the frames moving around on a microphone stand. So as you move around the environment, we could then render sounds in the environment that would then overlay on top of it to create a kind of augmented audio environment. And the whole idea is this acoustic transparency, is that we're easily mixing between the two, real world and the virtual world. You can have a look at the video if you want to see a bit more about that. So we did some user studies on this, and we've looked at different types of headsets. So ones where you have loudspeakers, where the headset is fully occlusive. You have loudspeakers on the outside, which can pass the sound through, versus ones like the frames I just showed, where they're not occlusive at all, your ears are open, and we try and mix sounds in. Trying to see how different types of headphones work, and then different types of audio. So how might you use different types of spatial audio in this in this augmented world that you're creating? So the thing that we found from our study, and the thing that I'm most happy with, is that participants heard some of the digital sounds that we created as indistinguishable from reality. They couldn't tell whether we created them or they were sounds from reality. That means we've achieved audio augmented reality. So they could not tell whether the sound was real or whether the sound was virtual. So that means we have achieved the goal of audio augmented reality, that we can add things into their soundscape. If we choose to make it sound indistinguishable from the real world, then we can do that. Of course, you might choose to have something which is clearly from the computer generated world. Maybe you want to have a message or a warning from your phone or something like that. But you can also augment the real world with extra things. So I can add sounds into the real world that don't exist. So one of our examples was, maybe I want to indicate the number of messages I've got waiting by the number of birds tweeting. So I can have more birds tweeting in the environment. Wouldn't sound like anything other than normal birds, but I can hear more birds tweeting, and that might indicate that I have more messages waiting. And that just sounds like birds in the environment. It doesn't sound like some artificial beep to warn me. It's just something that's overlaid very naturally on top of the real environment. So this is a really interesting thing. This gives us this personal, private, always available soundscape that I'm carrying with me. If my glasses had those speakers in them, I'd be carrying that with me all the time. So that gives me a display. Nobody else can hear it. It's private to me. Gives me a whole lot of advantages that I can then get information displayed to me without obstructing my eyes, which could be useful if I'm walking around the environment and try not to trip over or get knocked down. I can still use my eyes and look around. I can still hear things from the outside world. So if there's a truck driving by, I can still hear it. But I get the audio from our computer-generated world on top of that. Now, as I said before, that's very difficult to do with visual AR because the devices are expensive, they're bulky, and they can't yet generate computer-based objects which are indistinguishable from real objects. But with audio, you can do that right now, and it's not that expensive to do. So it's a very exciting time for working on audio augmented reality because you can do it right now. That we've been working on, which I think is relevant to the conference, is enhanced TV viewing. So here, imagine that what you could do if you were wearing a pair of those Bose glasses whilst watching TV. So acoustically transparent headphones allow a TV viewer to watch the TV but have an extra source of audio. So maybe I've got the audio from my TV speakers, but I can have extra audio from my own personal audio space that I'm wearing. So I can do private audio enhancements of the TV content that nobody else in the room would hear. So it doesn't affect other viewers and it doesn't affect their experiences. So that's an important thing. For example, if you currently wanted to watch the TV in 2 different languages, well, you have to choose one and then the other person would maybe be able to understand it. But perhaps with augmented audio reality, one person could be watching the TV sound in one language and I can be listening to it privately through my own audio environment through another language without disturbing them. You can see a screenshot at the bottom there of one of our experiments with Florian wearing a pair of the Bose frames I showed previously. So again, we've done some user studies to investigate how we might use this and investigated a range of different augmentations. So for example, mirroring something from the regular audio stream to your glasses. So in our study, we used a TV with stereo speakers. And what we did with the glasses is then mixed something from the surround mix into the glasses. So for example, one of our conditions was looking at enhancing the dialogue. So maybe we can present the dialogue closer to you through the glasses if you maybe wanted to enhance that without disturbing somebody else in the room. We also looked at enhancing some of the environmental sounds. So maybe to make it more immersive, you might have more environmental sounds presented to you. If you only have a pair of stereo speakers, that may give you more of that kind of full surround sound mix in your headphones. So it'd be a cheaper way of getting a full kind of surround sound set up than just by just wearing the glasses. Well, you may do other things. I mentioned the audio, the language one before, where you might change to a different language. So maybe my friend is watching the TV in French, and I put my glasses on, and then I can hear the English version. Or maybe if you've got visual impairment, but you're watching with a group of friends, you can be receiving the audio description through your headphones, whilst they're still listening to the regular audio, which you can of course hear as well alongside your audio description, and you don't disturb them by making them listen to the audio description too. Or maybe you've watched this movie 10 times before, your friend wants to watch it for the first time, so you overlay the director's commentary through your headphones whilst they're listening to the regular soundtrack, because you want to experience something new. So you can add this additional content on top without disturbing their viewing. So several people in a room could be watching the same thing, but all listening to different aspects of it. So we ran a user study, and there's lots of details in our papers about that. But the kind of key takeaways was that the audio augmented reality added kind of spatial realism and immersion when the sounds were mirrored through the frames. So people felt more immersed in the programs when the sound was coming through the frames. The sound is closer to you, creates an interesting experience. You can create a more surrounding and immersive experience than just with a pair of stereo speakers by the TV. Our viewers liked the personal control over the sound mix, for example, being able to enhance the speech channel and having that displayed just to them and not having to disturb other people with an enhanced speech channel. So that was well liked by our participants in our studies. The ideas of accessibility and language comprehension, again, were appreciated, that you could listen in different languages without disturbing other people nearby, and being able to kind of enhance your experience of repeated viewing by adding this additional information, for example, director's commentary or other things. So that added to the experience, and our users liked to be able to do that. The interesting thing is you can still share some experience with them because you've still got some of the surrounding audio coming in, but the audio which is really close to you around your ears gives you something different. So you have your personal experience. So a little bit of a summary of this part of the work. So these new devices mean that audio augmented reality is available now. So you can go out, you can buy headphones such as those Bose ones right now, and they can do really high quality augmented audio reality because the speakers in them are very good and they've got microphones in them. So you can do a very high quality sound. So they're not the same as bone conductance headphones, for example. You get much better quality out of these ones. You can create spatialized sounds through them. And they're much cheaper, and the technology is much more realistic than for visual augmented reality, where you might have to wear a HoloLens or something like that. So these devices allow you to create a kind of personal, private, always available audio space. You can have things in that audio space which are clearly different from the real world, or we can do things which augment the real world and in ways that people then can't tell whether it's real or it's virtual. So that's the kind of goal of audio augmented reality, or augmented reality in general. So it shows that we can really do that with the technology that we've got right now. And I showed one application for this idea of TV viewing with friends or family members, where you can get different types of audio to them, depending on what your needs might be. You know, if you have a visual impairment, then you can get the audio description that maybe your family members don't want, and you can do that without disturbing them, but with still sharing in some of the experience of being in the same room at the same time. The nice fact that they're not occluding your ears means that you're not cut off from the people around you and conversations they might be having and things like that. So a few conclusions from what I've talked about for the last few minutes. So I brought up this idea of multimodal interaction at the beginning. The idea there is that we're looking at how we can use all those capabilities that our users have, rather than just focusing on visual displays, ever larger visual displays. We can think about some of the other things that users can do, and our focus has been a lot on touch and hearing. So that allows a much richer interaction with technology. Rather than just using visual displays, you can augment the visual displays with other kinds of things if you want to, or go in a different direction and not use visual at all and have purely audio displays. So sound is often neglected in multimedia because of the kind of dominance of visual things. Audio's got a lot to offer. So these new audio technologies, I talked about the ultrasound, I talked about the headphones, they allow us to create highly novel interactive experiences, things that you can't easily do in any other way. For example, I talked about levitation. There's no easy other way to kind of create and levitate such and precisely control those physical pixels. People have done that with magnetic levitation, for example. That allows you to levitate larger objects, but you get much less control and your physical pixels can't be so small. So our idea is you can have very small pixels and control them very precisely to create very realistic 3D models. Then we talked about audio augmented reality, the fact that I can be wearing basically a pair of glasses which don't look anything different to normal glasses, but then I can have this rich 3D audio reality laid on top of the real world, and the really interesting things I can do with that. So that provides lots of new opportunities and new applications, new areas that that we can create experiences for. So my plea to you at the end of the talk is, don't forget the audio. There's a lot of things, interesting things that sound can do, and these new technologies allow us to do some great stuff. So thank you very much for listening. That was a talk about how to use sound for new multimedia experiences. My name's Stephen Brewster, and if you want to get in touch with me, then you can use the contact details below. Thank you very much.
Okay. I'm assuming we're already live. Hello, everyone. My name is Alexander Rake. I'm professor at TU Ilmenau on audiovisual technology, and I have the great honor to chair this very interesting discussion about the very interesting talk by Stephen Brewster. Hello, Stephen. Nice to see you here. Yeah, and we have quite a few questions in Slido, and I'd suggest we just directly jump into these. So the first one here on the list is, have you also thought about removing environmental sounds, for example, loud cars on the street when walking, with the AR, the audio AR next to it? And which challenges would you expect with this?
I think that would be a really interesting thing if you could do that. Then you could really control the environment even more. I guess a challenge is that the speakers on those glasses are not that powerful, so a loud truck driving by is likely to be louder than anything you could do with speakers. But let's think about sounds which are maybe less loud than that. So potentially you could do some clever filtering to remove some of that. That becomes like active noise cancellation, I guess. So yes, I think that would be an interesting, good thing to do.
Thank you. Okay, the next question is by Haley Hung, who was our keynote speaker yesterday. What are the technical challenges when scaling to pixel levitation to denser and more pixels? And what are your suggestions for solutions to overcome that?
So there are many problems. So it's difficult. So if you want to levitate a lot of pixels, that's fine. That's not a problem at all. If you want to move a lot of pixels around, then it becomes difficult. So if you just wanted a static object, say you wanted to create, a 3D model of a mouse to sit in front of you, you didn't want it to move, then you can levitate pixels into all of the nodes of the standing wave. So you can create quite a dense array. As soon as you want to start moving stuff around, then you have problems. An interesting thing that we're working on right now is obstacles. So if you think about digital pixels, if I drag something across the screen, they move seamlessly around because the pixels aren't real. If I have to move this pixel here, past this pixel here, well, something has to move out the way. And if this one has to move out the way, then maybe there's one down here. You kind of get these potential cascading effects. So it's not just about the density, it's also about how you control the movement of all these obstacle pixels. So you can, basically, if you want more, you just buy more of the ultrasound arrays, stack them up, and you can create larger spaces. That isn't the only problem. One of the reasons why we're really thinking about how we control and move these pixels very precisely is because you need that for larger arrays, and you want deformable objects and dragging objects around. So I think getting control of the sound field and being able to have those precise interactions is the thing that enables those larger flexible arrays.
Mm-hmm. Yeah, thank you. Okay, and then next question here on Slido is how accurate can we produce such haptic feedback location-wise, right? So I think it's similar. There are similar other questions, so I think it's wrapping up a certain aspect here.
So you can be very precise in terms of the position. You can control that to millimeter level. The thing is that each of you is basically you create a focal point by combining all those sound waves together, and that focal point is limited to about 1 centimeter in size if you're using 40 kilohertz ultrasound, which is the kind of ultrasound you get in your car bumper from those little microphones I showed a picture of. So it means you can very precisely position them, but they're 1 centimeter in size. If you used higher frequency ultrasound, you could potentially reduce the size, but for the speakers that we're using, it gives you 1 centimeter. So you can position that centimeter very precisely, but each one is a centimeter, and then you need a little gap around it before you have another one. Otherwise, you get interference between the focal points. So that kind of limits the resolution that you can achieve. But for an individual focal point, you can very precisely put haptics where you want, or do the levitation of the bead where you want. You can be very precise over that.
Mm-hmm. Yeah, and maybe I've let that follow by a directly related question. It's actually the second one here on this list, but it's directly related. So how intense is the haptic feedback, right? Your setup can create. So now you have been speaking about location, but now in terms of pressure, what kind of, can you compare that with weight or pressure?
Yes, it's pressure. You can feel the pressure against your skin. Now, remember, what you're doing is moving air against your skin. You're moving it very precisely, so you can't generate the force that you could generate from the motor in your mobile phone or something like that. So you're only pushing against air, so that gives it an ultimate limitation on how much force there can be. So you can create perceptible forces, you can create perceptible different textures and things like that, and so that is no problem. And as you can see, we can also use those forces to levitate polystyrene beads. You're not going to use those forces to levitate humans, for example, because they're far too small. If you want to levitate bigger things, then yeah, you can use electromagnetic forces, but they give you much less precise control. So the reason we use the ultrasound is because it gives us very precise control over those tiny pixels. And actually, if you want a high-res display, you want very small pixels. So there's limitations. With the forces, you can feel them, but they're it's like a strong jet of air against your hand. That's the kind of force we're talking.
Okay, very interesting. Thank you. The next question now here on the top of our list is how would you safely introduce such audio AR applications into the real world, especially in light of distractions or confusions, right, and surprises, right? Thinking about it myself.
Yeah. I mean that's a really great question, because we don't want to create dangerous situations. So the first thing that we were happy with is, of course, that those headphones don't occlude your ears, so that you can hear the world around you. So if you have fully occlusive headphones on, maybe like what Alex is wearing right now, then you could block out the environmental noise and then a truck driving by, you wouldn't hear it and you might step out into the street. So you don't have that with the headphones I was showing because they're completely open to the outside world. So that is a positive. And you can still do 3D sound through them because you've got the very precise speakers, which was difficult in the previous generations of headphones. Then you have the interesting issue of being able to kind of trick people into thinking that there are things in the environment that aren't there, or maybe as even the first question, masking things from the environment so that you can't tell that they're there anymore. So yes, I guess you have to be careful of that. That's something I guess we're only just starting to think about because we're only just able to do it. Of course, if you want to put things into the audio environment, you don't have to make them sound like the real world. You could have them sound different so that they're not mistaken for real world things. So I'm not sure I've got a good answer to that, except that yes, you're right. You should be careful over it. But I think we're still at the stage of learning how to make use of it and understand it and apply it. So I think that's a solution or a problem we need to find a solution for as time goes on.
Mm-hmm. Thank you. I think this is a very interesting topic, and especially one which leaves a lot of space for future research. How do you encode the information also in light of how the real world information is encoded, right? Because you cannot actually distract or basically block it out auditorily. Anyways, next question here. What are the key differences in measuring user quality or perception from a process perspective? So, and in particular, of course, what are the best techniques for these novel, when you apply this to these novel experiences you have been describing?
Yes. I'm not sure what from a process perspective necessarily means, but I'll give it.
I think it's referring to the methodology, methodological aspect of it. I'm presuming, right? I mean,
so maybe I'm coming at a slightly different direction from people attending the conference, because the cue of your conference, I guess, is quality. So I come from a human-computer interaction perspective. So we think a lot about usability and things like that. So we tend to measure the performance of the things that we do with things like the time taken to complete a task using it, or the errors you make, or the subjective things like satisfaction, usability, and those kinds of things. So the difference between quality and perception, maybe I'm a little bit unequipped to answer that question, because I come a little bit more from the perception side. So a lot of my background is from psychology, where we do kind of applied perceptual work. So we take something like the haptics and we see how people can experience and feel that haptics in lab settings, and we spend a lot of time trying to work out, well, what kind of experiences can we make there, what different textures can we design, what's the spacing around the hand, all those kind of things. Maybe less about the quality of the experience in the way that it might be thought of from the QoMEX conference. So that's actually something that would be interesting for me to find out a bit more about and talk to an expert in that kind of quality a bit more. But mostly we think about user experience. I'm not completely sure how aligned that is to quality in the kind of QoMEX world.
I think it's pretty closely related, and especially the term satisfaction is probably what we're after. We're just more applying it to this kind of multimedia quality aspect, right? Of which certainly your aspects also form a part in some way, right? But we're more coming from this traditional services, of course, right?
Yeah, I mean, efficiency, effectiveness, and satisfaction are the kind of three core parts of usability, which I guess do overlap a lot.
Yeah, I agree. Yeah, I think that answers the question quite accurately. Thank you. Then we have a question that I think that has already been addressed, right? I mean, how close can two different pixels be? I think that's iterating on something we already had. So I would go for the next one. That's actually something new. It's a bit of an advertisement question, right? So the Bose as an application example that you actually had, right? Those headphones / sunglasses you mentioned, they got mixed ratings. I mean, again, some kind of satisfaction or user ratings, right, in the field. Where do you see advantages,
so
over maybe other ones that are out there?
Yeah. I mean, I'm not, I'm not employed by Bose to sell their frames. I'm just a user of those frames, and we also use other technologies as well. Those ones just kind of have got my interest recently. So why are they good? Well, because you have the speakers spread out quite far around the head, you do get quite good spatial presentation. So you can do binaural sound through them and get quite good 3D sound. Now, I'm not expert enough with AirPods, for example, to know how good the 3D sound might be with those. The Bose ones also have an IMU, so they have the orientation sensing for your head, which we need in order to be able to spatialize the sounds and keep a sound fixed in location as you move your head or move about in the world. So they have that advantage as well. They have good battery life. I mean, and also they aren't in your ears, so they don't block them at all. Whereas perhaps even something with the transparency mode in your ear still blocks out some of the environmental sounds. So I think I'm not going to say that they're the ultimate and the best headphones in the world. They certainly do some things well, which is why we use them. But we've looked at bone conductance headphones in the past, and the quality of those is definitely worse. We've also done things with occlusive headphones, but with noise cancelling, and looked at those. But so far, it seems like the frames have given us the best mix of environmental sound and our own sound mixed on top. But that's certainly a work in progress, and I'm sure by next year there'll be a new version of something else, which we'll want to try. It's an ongoing and evolving area.
Yeah, and actually that brings me to another observation. Of course, mixing it with glasses already directly points us also to an aspect where visual AR can more easily be included, right? And I think it's an interesting direction to address this both in one.
Absolutely.
And I think actually the first two questions which we see here online now in YouTube are the ones which we kind of already addressed, right? Implicitly. So let's maybe move to that question, number 3 here. Where do you see the quality of those visual AR glasses, now and also in a couple of years? I mean, when would you think that something which actually combines your oral experience with bone conduction with some visual experience which has the same fidelity, let's say? I mean, I'm reframing the question myself.
Yeah. I mean, I think there's a lot of companies spending a lot of money making visual AR. So if you think of Magic Leap and how much venture capital cash that they got, presumably it was a lot, and Microsoft has spent a lot on HoloLens and HoloLens 2. There's rumors of Apple doing augmented reality. There's many other companies producing headsets. So there's a lot of work going on in that area. I think it's just that visual perception is differently difficult to audio, so it means that it's very difficult to get all that stuff working well. You need lenses, you need optics, you need fast processing for the graphics, you need the battery life to be good, you need them not to be too heavy. So I think there's a lot of clever people working on those things. So I think the answer to that question is, when do you expect it? I expect it all the time, because as soon as a new device comes out, it's better than the previous one. Even if you think in the world of VR headsets, there's a lot of change going on right now with manufacturers producing new ones all the time. We can only expect the same with AR. Now, the question might be, my bold claim was that now we can do full augmented audio reality and make the user think we can have something from our digital world which is indistinguishable from the real world. So when could we do that visually? That's the real question. And I think that's still quite far away to do in a form that you might want to walk down the street in. Again, not being a salesman for Bose, but those headphones, I've worn them. I've walked down the street wearing them. I didn't feel embarrassed. It was great. Would I do that with a Microsoft HoloLens 2? Well, probably not right now. So maybe as time goes on, that's going to get better, but there's a lot more problems to solve. So we're working in the area of visual AR as well, and we're doing interesting things in that area, but it's just not ready for prime time as the audio AR is, which is why I thought I'd talk about that today. But there's certainly a lot of innovation and a lot of research dollars going into visual AR.
Yeah, and actually, I think that most of the other things have already been addressed. Yeah, there's one more question which we don't see here on the YouTube, but maybe I have an own one now. And that is, have you tried out combining the two things that you have been presenting, right? I mean, I'm assuming that there are probably some synchronization aspects to be covered, right? Because you would be doing it with glasses on the one hand side and then with another approach for the, for the haptic aspect on the other. But do you have solutions in your lab where you are able to basically have sounding objects that people can play around with and touch? Is this something you're addressing?
So I mentioned the this levitation project as part of the slides there. So in the levitation project, what we're trying to do is ultrasound haptics, levitation of pixels, and parametric sound. Because that's just a speaker array, you could do parametric sound from that. So very precisely targeted sound. So the aim of the project is to do all three of those at the same time from the same array. And that's extremely challenging because you need three different sound fields. One for the levitation, one for the haptics, and one for the audio, or the sound that you're listening to. So, and that actually is, of course, a very difficult one, because if you want good frequency response, you need to change that. If you want 20 kilohertz frequency response from there, you need to be able to change that sound field at 40 kilohertz. And at the same time, you need to be able to fit in the sound fields required to levitate the particles and to generate the haptic feedback. So that's actually really difficult to do all at the same time. We can do it pairwise pretty well. So now we can do haptics and levitation, or levitation and audio. But doing all three is really challenging. But that's our kind of grand aim on that project. And that requires a lot of synchronization, control of the sound field, all sorts of different manipulations of the way we generate the sound. So that's very challenging. In terms of if you want to do augmented reality as well as the haptics, for example, that's not too difficult to do. You can use something like Unity, which is the kind of VR development environment. So you can create a virtual world there which you can feel. So one of the PhD students in the group, for example, has been looking at how you could create haptic experiences in VR, but not holding the controllers, but just putting your hands into VR, and then we can beam those haptic forces to your hands. So he's, for example, been looking at how you could change the roughness of objects to feel differently rough, so that you could experience different objects in the space and they would feel different. So we can beam those haptic forces to your hand, and you can see the objects, the virtual objects, through your headset. So that actually is not that difficult to do. One of the partners made a nice bongos game where you're playing bongos in VR, and as you hit the bongos, you can feel the haptic feedback, and you can feel effect on the bongos as you get high scores and power ups and stuff. So being able to tie those things together is that in itself isn't difficult, but combining more and more things, then that starts to get really hard.
Very interesting. Thank you very much. Yeah, and then I think a new question here is again from Heidi Hung. For the example of the cube rotating, how do you get the pixels to move across a column? And maybe you can explain a bit more about how the waves are basically being manipulated.
Yes, so the whole of that levitation work and the haptics, ultrasound haptics work, is really based on clever acoustics. And we have a great acoustics partner from Chalmers University in Sweden who are world experts on that. So it depends on which axis you want to move. So in the cube, it was rotating around like this. So that's relatively easy to do. You can control the sound field, and you can create snapshots of the sound field where with slight movements of the focal points, and as long as you don't move them too far in any between any snapshot, the beads are supported and move around quite nicely. So if you move in very small steps, then you get pretty smooth movement. The trickier one is, I think in the video I showed it rotating in this dimension. Now that's kind of harder because you then have to move beads in and out of the standing wave. So if you think about the standing waves are just moving up from the top to the bottom and the bottom to the top and making these nodes and antinodes. So the really difficult one is moving pixels that then cross over and out of the same columns, because then there's potential for interference, which is why you saw in one of the slides there, the one with the green background, that the pixels appear to wobble around a little bit more as they were in that orientation than when they were in this orientation. So that's a tricky one. So you have to be much more careful about your sound field design if you want them to move and cross into and out of the same vertical column of standing wave. So yeah, of course you can do it. We've shown it there, and as our algorithms improve, that becomes more precise, and less wobbly. But that orientation is always more difficult than ones where you're moving this way, where they never your pixels or even if you have two pixels here, they're just moving in the same positions, so you don't have to change the sound fields in such a complex way.
Mm-hmm.
Sorry if that was a kind of rambling answer to that question.
No, I think it was clear. And there's a directly related question with that. It was basically when the loudspeakers seem to always have been basically lying down flat. Whether you can also position them otherwise, right? I mean, I think that's directly related. Yeah.
No problem. Yeah, you can have them in different orientations. You could have the speakers moving, but you want the position of those two speakers to be fixed with respect to each other. Now you can do one-sided levitation where you just have one array at the bottom and no corresponding array at the top. That's less stable because the standing waves are then less robust, but you can still do that. And that's quite nice because if you want to kind of look into it and kind of interact a bit more, then you haven't got a kind of top in the way, but you do sacrifice some of the stability in order to do that. And the arrays don't have to be square, they can be different shapes. We've also investigated arrays with holes in them, so that, for example, you might have something in the middle and then an array around the edge of that, so that you could maybe have a visual display in the middle with pixels around the edge beaming forces. So again, there's advantages and disadvantages, but that tends to have to make the forces weaker. The more actuators you have, the stronger the forces are because you're combining more sound waves.
Mm-hmm. Very nice. Yeah, thanks. Okay, I see another question. I kind of have a little bit ignored it, so sorry for that. I have a personal answer to this, which is probably why I ignored it. So I'm asking this to you. So speaking of multimodality, do you personally draw a distinction between oral versus audio experiences, or do you consider them to be similar?
What do you mean? What is the difference between an oral and an audio experience then? I'm not quite sure what the difference is.
Yeah, I mean, people have rated this high, but I would also think that they are probably the same, right? I mean, they are the same. One is from the signal side, I'd say, right, the acoustic side, and the other is from the experience side, right? So depending on what your framing is, basically, right? Yeah. So to answer that
so maybe
question,
one's a signal, one's a perception. Yeah. Okay.
Yeah. I would argue that these are the two. That this is the distinction you could make, right? That's why probably I didn't ask that, but yeah. I hope the question is clear. Otherwise, please retype it. Maybe I have also, or we have misunderstood how it has actually been framed here.
Yeah. Whoever said that one, do we make sense of that?
Yeah, I hope so.
put another question on the slide out. You can tell us if we got that wrong.
Okay, yeah, I think that this is ending our question session. I think we have addressed everything. Please don't forget to join the socials, the social Zoom, right? So before you quit, I'd like you to remind you of that. But let's thank, with virtual applause, Stephen Brewster again. Thanks so much. A really super interesting talk and also super interesting Q&A session. Thanks so much.
Thank you for the great questions.
Okay, sorry, it seems we had some technical issues, but let's try this again. So hello to everyone, good morning, good afternoon, good evening, and welcome to today's oral sessions. So my name is Les Korinkapov from the University of Zagreb, and together with my co-chair, Peter Shelkins, we will be chairing today's sessions. So we have, the first session is on video quality, the second one will be on novel research directions. So to start off with, in this first block, we have three very nice papers addressing various quality aspects related to video streaming, and in particular, adaptive video streaming. So let me pass the mic now to Peter to introduce himself and the first paper.
Hello, good afternoon. My name is Peter Shelkins. I'm with the University of Brussels and IMEC. So let me introduce the first paper to you. It's actually a mouthful. So this paper is focused on the bitstream-based model standard for 4K UHD, ITU-T P1204.3, and it covers models, details, evaluation, analysis, and open source implementation. We have quite a large group of authors of this paper. So it's Rakesh Rao, Steve Goring, Peter List, Werner Orbica, Bernard Feiten, Ulf Wustenhagen, and Alexander Rake.
Hi, I'm Rakesh Rao, a PhD student at the Technical University of Ilmenau. I'll be presenting our work on the bitstream-based model standard for 4K UHD, its details, evaluation, analysis, and open source implementation, which was done in collaboration with colleagues from Deutsche Telekom. The open source implementation can be found on GitHub, the link to which can be found both on the slide and in the paper. Before going to the main presentation, I would like to give an overview of the presentation. I'll start with a brief motivation, followed by an overview of the bitstream models and the associated related work. Then I will talk about our proposed model, its training, validation, and evaluation, and wrap up my talk with a short conclusion and a few ideas for future work. In recent years, there has been an increase in higher resolution and frame rate videos which have been compressed with new codecs that have been used in streaming services. This gives rise to the need for video quality models capable of evaluating the quality of such contents. These models should also be applicable to a diverse set of video contents, and for this, the newly developed models should be trained and validated on large datasets. Also, to make sure these models are widely used, making them publicly available is a necessity too. Keeping in view all these requirements, let's now look at a brief overview of what kind of bitstream models can be developed and have been developed. Bitstream models can be broadly categorized into three modes based on the input information that is available to the models. These different modes are generically named as mode 0, 1, and 3, with mode 0 being the least complex variant with access to the metadata-based information such as resolution, bitrate, frame rate, and codec. A mode 1 model has access to all the features that a mode 0 model has, and in addition to this, also has access to the frame size and frame type information, thus making it a packet header-based model. The mode 3 model is the most complex variant of all the bitstream models and has access to the entire bitstream and can be viewed as a decoder-based model. Many bitstream models of varying complexity have been reported in literature to estimate video quality. Some examples are the models proposed by Shahid et al., where they use their models to predict pixel-based metrics such as PSNR, SSIM, etc. Kaimel et al. Proposed a mode 3 based bitstream model which uses QP values and frame types as input information. Recently, ITU-T has standardized the P1203 recommendation, which proposes a series of models ranging from mode 0 to mode 3. The defining feature of these models is that they address the HTTP-based adaptive streaming specific degradations. All these models, though, suffer from the drawback that they are not applicable for videos of higher resolution and frame rate which are encoded with newer codecs. To mitigate this, Rao et al. Propose an extension to the standardized P1203 Mod 0 model, which can be used as a starting step to develop newer models which can be applied to these high resolution and frame rate videos. With this knowledge, let me now present our proposed model. This figure represents the overview of our model. We use an hybrid approach in our model where we use the traditional curve fitting approach in combination with the machine learning based approach to predict the overall video quality. A proprietary multi-codec video parser is used to extract the features that are required as inputs to these models. Let's now take a deeper look at our proposed model. Let's start off by taking a deeper look into the curve fitting part, which we call the core model. This part of the model is based on the degradation-based modeling approach, and hence we define three different types of degradations, namely quantization degradation, upscaling degradation, and temporal degradation. Quantization degradation usually arises because of the chosen quantization settings during encoding and usually manifests itself as blockiness or other forms of coding artifacts. The upscaling degradation usually occurs when a lower resolution variant of a video is upscaled to the display resolution and is perceived as blurriness by the end user. Similarly, temporal degradation also occurs when a lower frame rate variant of a video is upsampled to the display frame rate and manifests itself usually as jerkiness. All these degradation values are expressed on a 0 to 100 scale and not on the traditional 5-point ACR scale in order to compensate for the compression at the scale ends of the 5-point ACR scale. Once these degradation values are calculated, the final prediction of the parametric part is then obtained by subtracting these degradation values from the pristine quality of 100 and then transforming it back to the 5-point scale. Once this is done, we use the machine learning part of the model to enhance the accuracy of our prediction. So, for the machine learning part, the training target is not MOS. That is the case with the parametric part of the model. Here, the training target is the residual, which the parametric part of the model is unable to predict. The machine learning part of the model in our case is based on random forests, which have 20 trees and a depth of 8. In our case, we define one random forest for each of the display device categories. There are two display device categories that are considered, namely PCTV and mobile tablet. As input to the random forest, in addition to the mode 0 features, we also use quantization parameter, average motion per frame, motion in X direction, frame size, frame type, and the parametric part output as additional input information. Using these additional input information, we then calculate the residual. And then the final prediction of the machine learning part is the summation of the parametric part output and the predicted residual. Finally, the overall prediction from this model is a weighted linear combination of the parametric part prediction and the random forest part prediction. In our case, we give equal weights to both these parts. Keeping in line the need for wide-ranging applicability, this proposed model has been trained and validated on a large dataset of 26 different databases with around 5,000 different samples. The duration of the samples were between 7 and 9 seconds. Subsequently, to independently evaluate this model, we use the recently published AVT-VQ-DB USD1 dataset, which consists of 4 different subjective tests and a total of 756 samples, with the sample duration ranging between 7 and 10 seconds. This plot shows the performance of the proposed model on the AVT-VQ-DB-USD1 dataset. As can be seen from this plot, the model performs very well on the dataset, both in terms of RMSE and Pearson correlation. We obtain an RMSE of 0.42 and a Pearson correlation of 0.94 across all databases. To get a deeper understanding of the performance of the model on individual database, we can have a look at the performance of the model on each database individually, and it can be seen that the model performs fairly well across all databases. To see where the performance stands in comparison with the state-of-the-art objective metrics, we compared the performance of the proposed model with the state-of-the-art objective metrics on the same dataset. We considered objective metrics such as WMAF, BRISC, NEAK, SSIM, etc. for our comparison. For both databases without frame rate variation and with frame rate variation, our proposed model significantly outperforms the existing state-of-the-art objective metrics. So, to conclude, we developed a More3 bitstream-based no-reference video quality model, evaluated this model on an independent dataset, and found out that our model outperforms the state-of-the-art objective metrics. In addition to this, we also provide an open source reference implementation of the model and the associated multi-codec video parser so that it can be used widely and for further development. As future work, we intend to develop a long-term integration model which takes into account HA-specific degradation such as initial loading, stalling, and quality switches, and then use our proposed model as the video quality part of the overall prediction process. We also intend to develop models for newer formats such as 8K, HDR, and also newer codecs such as AV1, VVC, etc. For more information on the coefficients of the parametric part and other related things, please do have a deeper look at the paper. Thank you for your attention. Sure.
Okay, great. Thank you very much to Rakesh for the very nice talk and for providing insights into the latest activities in ITU Study Group 12 and also together with WeQuake focused on developing models that are applicable now for different codecs and also in light of higher frame rates and higher resolutions as we see necessary for high quality streaming content and codec development. So we have a number of questions coming in on Slido. I'll read them back to you. So first of all, there's a question on whether or not the used evaluation dataset will become accessible, and also what about the training datasets?
Yeah, can you hear me?
Yep.
Unfortunately, the training databases are not available because this was part of the competition that we were in the ITU. But for the evaluation database, we already have made available a few months ago, so people should be able to access this. And there's a corresponding reference in the paper itself for this database.
Okay. So thanks a lot. We have more questions coming in. So in HTTP adaptive streaming, you include quality-related metadata, making it available to the client. Which data should be provided from the source to the client for QE?
I would say the ability to parse the entire bit stream would be necessary to use the model at the client. So since we use parameters like the quantization parameter and average motion, so if you're able to parse the entire bit stream at the client, you should be able to use this model.
So this would be necessary.
Yep, this would be necessary.
Okay, great. Thanks a lot. Let's see. Next question. Could you please comment on the performance of your model if it is used for predicting quality for HDR or light field videos? So would it be applicable in this context?
Obviously, I would say a small bit of an extension would be required, keeping in view the way encoding would be done for HDR light field videos. Since the encoding might differ, the model would have to be adapted for this. How major the adaptation would be dependent on what kind of data we have right now. So right now I can't say how good the model would be. We should be able to apply the structure of the model, but like I said, it depends on the encoding that we use.
Yeah. Are there plans already underway in this direction?
Yes, this is one of our future ideas for extending the model, as we saw in the conclusion work. So.
Okay. Maybe just a question also. So you said that this for the presented model is applicable for sequences or for segments that are 5 to 10 seconds in duration. But you also mentioned ongoing work. Now that we mentioned ongoing work, towards an integration model taking into account also initial delays, installing, and quality adaptation to predict this overall session audio-visual quality score. Maybe could you comment on let's say efforts in this direction also?
Yes, there are ongoing efforts. For example, at ITU, we already started a new work item where we would be interested in developing these long-term integration models. Like in the talk yesterday about this stalling for in music streaming, there was a question about, is there a necessity to change the subjective test paradigm to see if people can judge stalling well. So in this work item, we are having this as a multi-fold process where we will be looking into this analysis about the subjective test paradigm and also developing the models. So this is the current ongoing plan that we have.
Yeah, okay, great. Thanks a lot. I think we'll have to take the remaining questions offline. So thanks again to Rakesh and to all the co-authors. We'll move on now to the next paper. Unfortunately, Peter is having some technical problems, so he's not here. But I can introduce it. So now we're looking at the impact of different user interactions in quality estimation models, also for adaptive video streaming. So Ivan, the floor is yours.
Hello everyone, greetings from Zagreb. My name is Ivan Bartolec, I'm a PhD student and I will present you a paper entitled Inclusion of End-User Playback-Related Interactions in YouTube Video Data Collection and Machine Learning-Based Performance Model Training. As you can tell by the long title, this paper expands on the body of recent research that has addressed QoE monitoring of HTTP adaptive video streaming, in particular from a network provider's perspective. With major streaming providers employing traffic encryption mechanisms, network operators are faced with the challenge of monitoring end-user quality of experience. Throughout the years, several studies have been published that investigated the potential of exploiting machine learning techniques for QoE estimation. However, the majority of these studies tend to idealize the viewer's behavior by playing videos without any kind of user interactions. ITUT recommendation P1203 specifies model algorithms for monitoring media session quality for TCP-type video streaming. However, the recommendation states that user-initiated interactions are out of scope, or more specifically, pausing, seeking, user-initiated quality change, user-initiated play, or user-initiated end are all not considered. However, when we consider realistic scenarios related to user behavior, we know that users commonly invoke some form of interaction with the video player, such as pausing or seeking. This raises the question of how to predict the QoE or relevant key performance indicators of video session with active user behavior, having access only to encrypted traffic flows in the network. Assuming we are using a machine learning approach to estimate QoE and/or KPIs, the question further arises as to what are the implications of various types of interactions on the prediction outcome. In our previous research, we have investigated to what extent machine learning models trained on data without user interactions are applicable in scenarios involving basic user interactions, and the results have shown a significant drop in model performance. While certain user interactions may be driven by poor service quality, they may also indicate a loss of interest in the content being viewed. Our focus in this paper is not on analyzing the root causes of user interactions, but rather on investigating the potential for network operators to monitor key performance indicators in light of realistic user playback interactions. Given the wide range of different interactions, various combination of interactions, and different time points of interaction execution, we provide a methodology for systematical investigation of the performance of machine learning-based KPI estimation models trained on data with certain user interactions, and identify which subset of interaction types have to be included in model training, so as to optimize the overall data collection and model training process. Such results can provide valuable insights when instrumenting automated data collection solutions. With respect to our test methodology and lab setup, we collected application-level ground truth data as well as the network-level data for over 700 YouTube videos not longer than 10 minutes, played on the native YouTube application on a mobile device. The majority of collected videos include one or two interactions which were manually triggered at a certain phase of video playback. The extracted machine learning features were labeled with the ground truth target variables calculated on a per video session basis. A total of 17 machine learning-based models were trained by using the random forest classifier, with the number of trees corresponding to 1000. 3 user interactions were addressed in the scope of this work: pausing the video between 15 and 40 seconds, seeking forward to the unbuffered part of the video, and video abandonment. Additionally, 2 different video playback speeds were addressed: playing videos in half of the normal playback speed, and playing videos in the double the normal playback speed. In total, 6 datasets were collected. Dataset None, which contains video sessions without any user interactions, Dataset Pause, which contains videos with 1 pause interaction per video, Dataset Seek, which contains videos with 1 seek interaction per video, Dataset Abandon, which contains videos with abandonment interaction, Multiple Interactions dataset that contains a combination of 2 aforementioned interactions, and Speed Interactions dataset that contains videos with changed playback speed. In the next 3 slides, we present the performance of trained machine learning models. Each column in the table represents model performance in terms of classification accuracy for models trained on dataset X, while each row of the table represents the classification accuracy of different models validated on datasets Y. For example, in this column, X represents a subset of datasets None and Abandon, on which model was trained on. Similarly, in this column, X represents a subset of datasets None, Pause, and Seek, which were used for model training. The first row represents a subset of datasets on which the model was validated. It is comprised of datasets None, Pause, Abandon, and Seek, and excludes the subset of datasets used in X. For example, performance of the highlighted cell was given by the model trained on dataset None and validated on subset of datasets Pause, Abandon, and Seek. The second row represents the model performance when validating the model on multiple interactions dataset, and the third row represents the model performance when validating a model on speed interactions dataset. The top right cell represents model accuracy of the combined dataset split into training and test set, and in cases when the total number of resampled classes used for training was very low, we refrained from training models, and the performance of those models is represented as NA. For the longest resolution KPI, we used binary classification, with each video session classified as either HD or SD video. The lowest accuracy was obtained when the model was trained on dataset without user interactions and validated on dataset that contained user interactions. The highest model accuracy was achieved when the model was trained on datasets None and Seek, and was closely followed by models trained on dataset None, Pause, and Seek. Similar results are obtained when validating models on multiple interaction dataset. This leads us to the conclusion that data collected in light of seeking interactions may be a sufficient addition to the data collection and model training. Furthermore, an investigation on selected machine learning features has shown a possible influence of longer video pauses on model accuracy, indicating the need for future investigation. The performance of models that classify initial delay into 2 classes is displayed in this slide. User interactions generally do not impact the initial delay duration, as they occur afterwards. However, user interactions may have an impact on initial delay classification due to the fact that certain features are derived based on statistics calculated across the whole or part of the video session. The difference in performance between models is not high, with highest accuracies obtained for models trained on dataset None. Low classification accuracy throughout the whole table mostly indicate a need for identifying new features. Average video bitrate KPI was also classified into 2 classes, as either high or low. We observe that all accuracies are greater than 90%, with highest accuracy obtained for model trained on subset of datasets None and Seek. Average video bitrate is generally highly correlated with throughput, which is confirmed by large number of throughput-related features, and thus explaining high model performance. These results indicate that it may be sufficient to use a dataset without user interactions. To conclude, these preliminary results for YouTube videos played using the native YouTube app on a mobile device show that the impact of interactions highly depends on the KPI being classified. In certain cases, the model training process may be simplified by reducing the need to consider user interactions, while in other cases, various interactions impact relevant features and thus should be included when training models. Further inspection of selected machine learning features used for model training and the inspection of obtained accuracies, precision, and recall leads to the conclusion that including longer pauses and abandonment scenarios would likely lead to improved model performance. The question arises as to whether there is a need to derive new features that would be interaction agnostic. Such a possibility would simplify the model training process and aid in achieving model applicability across real-world settings. In our future studies, our focus will be on automating user interactions, primarily on mobile devices using the native YouTube application, so that we could provide a more comprehensive feature analysis across larger datasets, which would include different types of user interactions, including data collected in both real networks and in a lab environment. We plan to consider KPI classification across more than 2 classes, as well as consider real-time KPI classification. Thank you for your attention. We hope you found these findings useful and that you've enjoyed the presentation. All datasets are made freely available to the research community on the link below, as well as the full list of features used for model training. If you have any questions, feel free to send me an email.
Thank you, Ivan, for this nice presentation. I notice some questions are coming in, and so one question I see here popping up is related to the question of overfitting, since you are using a high number of trees. So, is this an issue in the system that you are presenting here, or did you are you having any checking mechanism installed actually in your algorithms?
Well, what I can say about this is that there is always a chance of overfitting happening, and especially when you have a lot of machine learning models trained, as we have in this paper, and when you don't have that large amount of data, of course, and when you use this large amount of trees in a random forest algorithm. But I think that we should be fine because I think that most of the trees had the same depth, you know. So in that case, I don't think that overfitting happened, but of course, I cannot guarantee it, and maybe we can check it if, you know, later on.
Thank you. So the next question is whether the data set is publicly accessible. So that's probably the $1,000 question that you always get.
Yeah, that's a very easy question, and this question was answered in the last slide. So if you rewatch a video, you can find a link to our data set on our laboratory website, right?
Okay, is it also included in the paper?
It's also included in the paper, yes.
Good. So you considered the longest play resolution in 2 classes, HD and SD. So how does your approach work with the typical YouTube resolutions?
Okay, yeah, thank you for this question. It's a very nice question, and we haven't checked this, but we plan to check it. Like we plan to expand on this research. Our first goal is to collect a large amount of data that consists of multiple resolutions, right? So we can basically check it and have a more elaborate analysis with it. But for now, we haven't checked it. Obviously, now when we have only HD, SD, right, binary classification, the results are a bit higher, you know, but I can only assume that when we have multiple classes that the accuracy would be a bit lower, right? Especially between some of the, let's say, neighboring resolutions, right? But I honestly don't know, right?
So let me ask you one last question. It's not in the list, but you mentioned that it would be interesting to search for new features that would be interaction agnostic.
Yeah.
So can you lift the curtain a little bit and explain in which direction you are thinking here?
Well, first of all, we want to move on from this per video session KPI or QoE classification. We want to move to the, let's say, live stream, or not live stream, real-time KPI and QoE classification. And basically, we are currently looking into it right now. So I cannot tell you more about it, but as soon as we found something, we will publish it, of course, and I hope it's going to be on the next QoMEX.
Okay, thank you. We're looking forward to this. So I guess we can move now to the next paper.
Thank you.
Okay, so thanks again to Ivan. So we'll stay on the topic of user behavior. Our next paper addresses the actual difficult task of trying to identify reasons for viewer abandonment when watching adaptive video streams into reasons that are more quality related and those that are content related. So along those lines, the authors propose a viewing abandonment reason classification model. The paper will be presented by Shoko Takahashi from NTT Network Technology Labs in Japan. So Shoko, the floor is yours.
I am Shoko Takahashi, working at NTT in Japan. Today, I'd like to talk about classification of viewing abandoned reasons for adaptive bitrate streaming. Adaptive bitrate streaming services for mobile terminals have spread dramatically with advances in the development of codec, video streaming, network, and display technologies. In adaptive bitrate streaming, videos are encoded at different quality levels and split into chunks, and video players enable smooth video playbacks by dynamically adjusting delivered bitrates on the basis of the throughput and buffer usage. However, viewing abandonments still occur due to not only quality degradations but also a lack of users' interest in contents. For example, if you find the content is not interesting, you will soon quit watching it. If you are interested in the content, you may continue to watch it even if the quality is a little poor. No matter how much you are interested in the content, if the quality is too bad, you will stop watching it. Quality-induced and content-induced abandonments are mixed in users' abandoned behaviors in this way. Many researchers have investigated the impacts of quality factors on abandonments. Others have also investigated the impacts of content factors on abandonments. However, as stated above, it is highly likely that quality-induced and content-induced abandonments are mixed in such behaviors. Therefore, some researchers have started to investigate the combined impacts of quality and content factors. However, quantitative evaluations are not finished yet. From video streaming providers' point of view, viewing abandonments should be prevented by appropriately designing and controlling video quality. To do that, the impacts of both quality and content factors on abandonments need to be quantitatively understood. As a first step to address this problem, we developed a viewing abandoned reason classification model that classifies viewing abandoned reasons into quality or content on the basis of feature variables related to application quality, users' operation behaviors, and the attributes of viewed contents. To build a viewing abandoned reason classification model, we conducted viewing experiments on adaptive bitrate streaming. The training and validation experiments were performed for different participants at different times. Under the controlled network status, a 10-minute test was conducted 5 times for each participant. In the experiments, participants were instructed just to view videos freely on smartphones. By using a measurement tool built into XPlayer 2.5.1, the behaviors of video players and participants were tracked. A question of asking the viewing abandoned reason was asked every time a session was finished. 23 videos were prepared for the training experiment and 49 videos for the validation experiment. Video files were encoded at 6 quality levels using H.264 in order to generate quality fluctuations. Audio files were encoded at 142 kbps using AAC-LC. In the experiments, by combining 7 throughput levels, initial loading delays, stalling events, and bitrate changes were generated. Various patterns of throughput fluctuations were generated and applied in the experiments. There were 160 participants, and the 10-minute test was conducted 5 times for each participant, so the total number of tests was 800 for both the training and validation experiments. The number of collected sessions was more than 2,000 for both experiments. Since the participants were allowed to view as many videos as they liked during each test, the over 2,000 collected sessions outnumbered the 800 tests. The feature variables related to application quality, users' operation behaviors, and the attributes of viewed content were extracted from view logs collected by the measurement tool. From statistical and machine learning models, 4 types of binary classification models were selected, developed, and validated: logistic regression, classification tree, random forests, and support vector machine. Since the SVM model showed a relatively high accuracy and did not appear to be overtrained, let me introduce the validation results of this model. This is a confusion matrix of the SVM model. In this matrix, the actual abandoned lesion is taken for the row header and the predicted abandoned lesion is taken for the column header. Here the number of correctly classified sessions is 604. The number of collected classified sessions is 273, so the accuracy of this model is about 70%. To figure out the features of the incorrectly classified sessions, we conducted Wilcoxon-Langsam tests where the feature variables were compared between the correctly and incorrectly classified groups. First, Wilcoxon-Langsam tests were applied to the actual quality-induced abandoned sessions. Here, we focused the test results on the feature variables related to application quality. The variables marked SD and NSD in the test result column were judged to be significantly different and not significantly different at the 5% significance level. The mean difference column shows the value obtained by subtracting the mean value of the correctly classified group from that of the incorrectly classified group. Thus, the variable with a negative mean difference is significantly lower in the incorrectly classified group. Let me take the stalling ratio and stalling frequency as examples. Focusing on the actual quality-induced abandoned sessions, the results indicate that these stalling-related variables take significantly lower values in the incorrectly classified group. This means that abandoned sessions with a relatively low level of stalling tend to be classified as content-induced even if they are quality-induced. And inferring from the fact that abandonments occur due to quality, regardless of the low level of stalling, it is considered that the impacts of stalling events cannot be measured by these variables. Second, Wilcoxon-Langsam tests were applied to the actual content-induced abandoned sessions. Again, the stalling ratio and stalling frequency are taken as examples. This time, focusing on the actual content-induced abandoned sessions, the results indicate that these stalling-related variables take significantly higher values in the incorrectly classified group. This means that abandoned sessions with a relatively high level of stalling tend to be classified as quality-induced even if they are content-induced. And inferring from the fact that abandonments occur due to content, regardless of the high level of stalling, it is considered that such behaviors must have occurred due to both quality and content. In conclusion, based on viewing experiments, we developed a viewing abandoned lesion classification model. 4 types of binary classification models were validated. The SVM model was considered to be the best, since it obtained relatively good results and did not appear to be overtrained. The results of Wilcoxon-Langsam tests suggested 2 directions for model improvement. One is to define explanatory variables, particularly stalling-related variables, and the other is to review the current method of asking about viewing abandoned lesions. Thank you.
Okay, so thank you very much to Shoko and all the co-authors for the very interesting paper. Let's start with questions. Maybe just a question in the beginning from my side. You mentioned you used this simple questionnaire to ask participants whether they are abandoning because of either content or quality. But in a real world setting, there may be additional reasons why someone may abandon viewing, such as having to attend to other business, maybe leaving a train ride or so on. Do you plan to extend this work in the future to maybe conduct some field studies or to look at these additional reasons beyond just these two?
Yes, I think in the future we need to we need to investigate the users' abandoned behaviors under the real world, under the real network conditions. And in the real world, users have many reasons to abandon their viewings. But as a first step to as a first step, we made a simple experiment to build a model of just classify viewing abandoned reasons into two factors, quality induced or content induced.
Yeah, okay. I think this is also along the lines of this question that we have coming up in Slido here, saying that since abandonment is also strongly influenced by context, how do you deal with potential bias caused by this artificial lab setup? So yeah, this question again going towards the need to conduct, I guess, field studies, right? Yeah, in the future.
Yes, of course, I think there are two ways to measure abandoned behaviors. One is to measure in laboratory experiments, and the other is to measure in the real world. And the first way is includes bias, but I know that. But I think we need to investigate the viewing abandonments of their users and compare the two models of viewing abandon classification models under laboratory experiments and real world.
Yeah, okay, great. Thanks. Peter, any more questions? You want to jump in?
Yes, in your presentation, you also mentioned the content attributes. And so I was wondering, and actually also somebody in the public was wondering how actually these content attributes are related to the quality effects, because this was not explicitly reported in your study. So can you give us some more insight on this aspect? So the relationship between the content attributes and how the and on the relation to actually the abandonment behavior.
Your question is about the relationship between content attribute and
yes, and the perception of quality, and linked with that, the abandonment behavior of the users.
We considered as content attributes just genre and number of viewers and average viewing time ratio. Genre and popularity attributes. So content attributes are not enough in this experiment, and we can measure. I think we had better collect more content attributes in the future, but in this research we could know that only the genre and popularity of contents can influence the abandoned behaviors. these variables were used as experimental variables of our models.
Thank you for your nice talk and answering the questions. I believe we have now a short of 5 minutes, and we'll be coming back after this break. So I hope to see you all again within a few minutes.
Thank you, Shoko.
Thank you.
So, welcome back, everybody. My name is Milene Farias. I'm from the University of Brasilia, and I'm one of the TPC chairs. I'm filling out for Leia now for this session. And now I'm going to go over and hand on to Peter so that he can introduce the next paper.
You drive me crazy. Interactive QoE assessment for telepresence robot control. So this paper will be presented by Hamed Jahromi, Ivan Bartolek, Edwin Gamboa, Andrew Hines, and Raymond Such.
Imagine if we could teleport human beings.
It means a new perceptual dimension.
I could actually play with my niece in Colombia.
Wow, that would be really awesome.
I could go to a conference and still spend less time flying and more time with my family.
We would have to redefine telepresence.
This is Hamed Jahromi. I'm a PhD researcher from University College Dublin. On behalf of our team, I'm going to present interactive QoE assessment for telepresence robot control. Telepresence robots, or TPRs, are remote-controlled wheeled devices with internet connection. A TPR can teleport you to a remote location, let you drive around, and interact with people. A TPR user can feel present in a remote location by being able to control the robot position, movements, actions, voice, and video. TPR facilitates human-to-human interaction whenever you want and wherever you want. The robot operator sends commands to the TPR by pressing buttons or keys from a keyboard, mouse, or joystick. Over the last years, people from different environments are benefiting from TPRs to attend a class, roam around the office, and visit patients, which is especially trending at the moment with COVID-19 pandemic. However, there is a research gap from QoE perspective that has to be closed. TPRs have a remote navigation aspect that represents the additional dimension when compared with conventional stationary audio-video teleconference systems. Navigating a TPR may pose challenges to the end users and influence their perceived quality. For instance, when a TPR operator is driving the robot, the operator expects an instantaneous reaction from the robot. However, an increased delay in sending commands to the robot may impact the robot mobility and the user's satisfaction. In this research, we are interested to understand how the network factors influence the operator's QoE when using a TPR in an office context. Before we look into the research questions, it's important to note that the TPR navigation is perceived visually via video streaming. So, in the first research question, we are going to focus on the TPR navigation and understand how the network factors such as bandwidth, delay, and packet loss impact the navigation QoE of TPR in an office context. We chose the office context since it is one of the most common indoor scenarios for wheeled TPR usage. In the second research question, we investigate to what extent do the users discriminate between navigation task quality and video streaming quality. Finally, we look into the influence of task types such as driving, turning, and parking on the TPR QoE. Now, let's look at the QoE study. The QoE study participants were situated in a laboratory setting in Dublin, Ireland, where they navigated a Beam Plus TPR via keyboard input on a desktop computer. The TPR was placed in a real office setting of California Telecom Company in California, United States. Bandwidth, delay, and packet loss were manipulated on the operator's PC. As presented in the table, each network factor has 4 associated values to emulate different levels of quality. The best quality condition presented here as level 4 and lowest as level 1. The study consisted of 23 test scenarios, each featuring a specific network condition and a specific navigation task. A total of 23 subjects participated in our QoE lab study. 8 subjects were female and 15 male, and the average test duration was 30 minutes per participant. 69% of participants were unfamiliar with TPRs. 22% had heard of them but not used them, and only 9% had a small amount of prior experience. We followed ITUT recommendation BT500 and detected 3 participants as outliers which were excluded from subsequent analysis. A post-test survey shows that none of the participants reported task boredom as a factor. In fact, they enjoyed the experience. Let's look at the result of our QoE study. With regards to the first research question, all 3 network influence factors have significant impact on navigation QoE, but in different ways. Bandwidth shows no influence on navigation QoE under a threshold of 9 megabit per second, while 1% packet loss has noticeable impact on the navigation QoE. And also, the result of mixed model ANOVA analysis shows that the impact of the different network factors on navigation quality rating is statistically significant. From the figure, we can also see that the absolute level of navigation QoE mass, as well as their sensitivity to network impairment level, depend on the actual impairment type. For the second research question, our investigation shows that the subjects are capable of discriminating between video quality and navigation quality. They treat them as separate concepts when it comes to experience assessment. Based on the ANOVA analysis, we see that the impact of bandwidth and packet loss on TPR video quality rating is statistically significant. However, delay is not. A comparison of navigation quality and video quality subplots shows that changes in mass across different impairment levels diverge between the two in terms of amplitude. To quantify this divergence, we performed a Spearman rank-ordered correlation coefficient analysis, revealing a weak correlation between video and navigation quality. The answer to our third research question is that the type of TPR task has more impact on the navigation QoE than the streaming video QoE. Based on our statistical analysis, we can understand that the actual task affects QoE sensitivity depending on the network impairment type. For example, the interaction between bandwidth and task is statistically significant for navigation QoE, which means that changes in bandwidth were rated differently depending on the task type. On the other hand, this was not the case for delay and packet loss. Regarding video quality, we did not see a significant impact of task on QoE sensitivity, except for the borderline case for packet loss rate. From this research, we have 3 solid findings. First of all, we understood that the users can differentiate fairly well between visual and navigation aspect of TPR operation. Second, all 3 network factors have significant impact on navigation QoE. Last but not least, depending on the actual task at hand, visual and navigation QoE sensitivity to specific impairments correlate weakly with each other. Let's have a quick look at the challenges and outlook. Since navigation is the novel feature of TPRs, we intentionally focused on QoE assessment of TPR navigation, omitting other aspects such as social interaction, presence, and embodiment. In this study, we didn't examine combinational impairments and we assessed each network factor independently. We believe that our study methodology and design, including task types, work very well and can be a solid basis for the future TPR QoE study. We also foresee the development of a more generic, empirically validated TPR QoE framework. Finally, it will be useful to investigate viability of using QoE models and frameworks from other related domains such as gaming and VR for TPR QoE. Thank you for your attention.
Okay. Okay, so we are back, and congrats, Hamed, on the great work. We have a couple of questions arriving, and so the first one that I'm seeing here, which is interesting, someone asking what mechanism did you use to filter out your experiment response?
Okay, thank you. It's a very interesting question because basically when we ran this experiment, we have considered a few like kind of methodological aspects, and also we consider ITUT standards like BT500. And the main factor which we also consider while we were filtering the three participants that we filtered from the analysis was those who didn't follow the methodology that we stated and we have given to the users through the training. So, and based on the hidden references that we had in the experiment, so we could identify the outliers and exclude them from further analysis.
Okay, thank you.
So did you also check how the familiarity of with the application impacted the responses?
Yeah, you know, we had a questionnaire that the users and the participants filled prior to the study. And the fact that we had a training before the experiment, I've done a few subjective studies, but this one was one of the most interesting ones in which the users were willing to participate in the study. And during the training, they paid a lot of attention to learn how to use the robot and how to drive around. And, you know, they didn't want to give up. It was like a gaming or something that the user really paid attention to the training, and we were recording the whole study, the video screen, and we were recording the study, and we noticed that the users did very well when they were trying the tasks, and considering the task durations that they have finished, they're almost within the same range of doing the tasks. So the training was very effective in terms of getting all the participants up to speed.
Okay, so there is one question which is related. Someone asks if, you know, the familiarity with the application or maybe gender and age impacted the, you know, the responses to your experiment.
Yeah, very good question. Basically, in terms of the familiarity with the application, we have given a thorough training to the participants. So they were all trained prior to running the user study. So that was not a problem, as the operating the TPR was very easy, like that they just need to use arrow keys to move the robot. That was in regards to the familiarity with the application. In regards to the gender, we have looked at the genders. We didn't find a strong impact of the gender in the mixed model ANOVA analysis that we have done, but we have seen some like small user influence on the results that we will definitely look into it in our future studies and see what would cause that.
And I think following this question, there is another one on how your methodology would translate to video games, which I think is kind of very related today. That's why I kind of like the other question, because it's you see in game that when someone is used, so there is a different response. So I'm wondering what is this relationship?
Yeah, actually, it's a very interesting question, because at the beginning, when we started to run this study, we said, okay, there are a lot of similarities between VR, gaming, and this user study, that we can have a benefit from them. But there's one thing which is really different, that is the TPR has a physical object which actually exists in a far location that impacts the perception of the users. Like in a VR and gaming, you are in a virtual environment, but in this, you are interacting with this physical, and we are physically influencing the remote environment. So it's a bit of different that we see from this, and we are sure we can imagine that these findings are also going to be effective. I mean, it's like kind of a two-sided things that we can have a benefit from the VR and gaming as well as the other way around.
Yeah, that's good. So we have time for one more question, I think. No? So there is one question here. Could be, let me see. I think I'm going to the most voted here. Why did you focus on navigation and maybe not on social interaction?
Okay, yeah, that's perfect question. Basically, one of the things which is different in a TPR navigation is the operator. Okay, if you look at the other side of the TPR, the users are seeing the screen mounted on a wheel device. Okay, so for them it's like they have a Zoom call, but the navigation gives a freedom to operator, so the operator feels present in the remote location and has a freedom to roam around. So that's a new factor that has a like kind of new perceptual dimension that we found it interesting to see that how can we estimate that and how can we quantify that using technical factors. And this is the first study. We had to do the first thing first. And of course, there are different dimensions and different, like as we stated in the future works that we can focus on.
Okay.
Thank you, Ahmed.
So we'll go back to the next paper. So the next paper title is Accessing Interactive Gaming Quality of Experience Using a Crowdsourcing Approach. This is presented by Steven and the other authors, and this is from the University of Berlin, Germany.
Hello everyone, my name is Steven Schmidt from the Berlin Institute of Technology. I'm a researcher at the Quality and Usability Lab, and together with my colleagues Babak Naderi, Said Sabet, Saman Satodajat and Sebastian Möller, I was working on assessing interactive gaming quality of experience using a crowdsourcing approach. Now in the following I will explain you a bit more about the motivation behind this research. I will give you information about a crowd gaming framework we developed and give you insights in a series of studies we conducted using this framework. Finally, I will conclude the talk with the major findings. Now, I think probably most of you already conducted a subjective test for various reasons. Let it be the evaluation of a system or maybe gathering data to develop a prediction model. Typically, we distinguish here between field studies, crowdsourcing studies, and laboratory environments. While the first two offer more realistic use case scenarios, typically we use the lab environment for these subjective tests as it offers a higher control about test conditions and means to directly observe the participants. So what you can say based on that is that it's a trade-off between validity and reliability that we are doing when we select such an environment method. If we would use a method of crowdsourcing, we can actually argue that these results would be more valid, as they represent the usual natural scenario in which a user would in most cases use a system. However, it's really difficult to get reliable data as you have no control about network conditions and what the user is doing. Now there are several disadvantages also from laboratory tests, such as that they are very time consuming and costly, and that the variability of users is low. This is something where crowdsourcing can really help us. Here you can assess a large amount of data in a short amount of time, and you have access to a demographically diverse audience. This view might be a bit biased, as I want to motivate you to this work, but just think about a sudden outbreak of a virus pandemic and you would not be able to conduct any subjective tests anymore in a laboratory environment. Right? So you can see that this method of crowdsourcing indeed, especially at our current time, is a very helpful method. Now the idea behind this research was to combine two recently published ITUT recommendations about the usage of crowdsourcing, P808, and gaming quality assessment, P809, with each other to kind of make sure that we can assess reliable data using the crowdsourcing method. This is possible to be used for not just quality assessment, but also for usability tests, playtesting, and the development of questionnaires, which is something that we also did with the data we gathered here. Finally, we wanted to check if this method is suitable by comparing the crowdsourcing and laboratory results with each other. So the crowd gaming framework is a bit lengthy, and that's why when you want to know more information, please have a look to the paper. I will just quickly go over the main components. So the ideal scenario of this framework would be when you have an open source game available, because This allows you to artificially introduce network or encoding degradations to the game itself. So for example, a delay could be simulated by just buffering an input event for X amount of time. Next, it would be really beneficial if the cord workers don't have to install a client to play a game. That's why we decided to use a web-based game, actually 6 web-based games developed with JavaScript, and of course there are also other means such WebGL, or you could even think of using cloud gaming and monitoring a network. We gave proper instructions according to these recommendations to the participants, but we did not want to trust the goodwill of the participants, and that's why we also introduced an engagement check to the system. Input information about the behavior of users was stored, meaning how often did they click, how often did they use the keyboard. And then we calculated a view threshold that represents a typical gaming behavior, and if people did not interact properly enough with the system, they were told to repeat a condition. This was really helpful to remove participants that did not pay enough attention to the gaming task. Furthermore, we used the token system to link data on a server, such as this input information, with those from the surveys, and the data, of course, was controlled with trapping questions, consistency items, and an outlier detection. Now, we conducted a series of 5 subjective tests. In the first 4, we investigated the parameters network delay, encoding frame rate, packet loss, and game feedback on gaming quality of experience using the crowdsourcing method we developed. In the 5th study, we compared parts of this data with laboratory tests. As a dependent variable, we used not just the overall gaming quality assessed here with a 7-point continuous rating scale, as we typically do that in gaming research, but we also used 3 out of 9 trapping questions for each condition. 3 of them here are shown as an example, where they also are different in terms of how obvious they are. So those that are targeting information about the gameplay, they are probably less obvious than the later question described here. Then we also had 2 consistency questions, and this is just a repetition of other items used in this question. Those items, by the way, assess the 3 concepts: responsiveness, controllability, and immediate feedback. Those were derived from literatures and from experts, and we wanted to also, as I mentioned, as a side project, use this method to reduce the item pool to develop a short item questionnaire to assess input quality. An item for responsiveness is shown on the scale below. In total, we had 571 workers, 42% of them were experienced gamers, 43 of them female, who participated in our tests. This resulted in 1,713 ratings, where the consistency check and outlier detection removed a small part of these ratings. However, the trapping questions lead to a really substantial drop in valid ratings, as we removed all these ratings where in one condition more than one trapping question was answered wrongly. Now, coming to the results. In the first test, we saw that there's an interaction effect of game and delay. This is not surprising, as many games behave differently in terms of the delay sensitivity. This is something that becomes very obvious at delays at around 150 to 200 milliseconds, and this is also seen here because some of these games that are more degraded are shooting and fast-paced games, while the others are not. For the frame rates, we could see that we can find a significant influence for the 10 frames per second condition compared to the others, but not between 30 and 60. This is something that confirms also findings from our lab studies. For the packet loss condition, we can see a strong degradation when there was an input packet loss simulated. This, of course, is also in line with traditional lab studies, and a significant drop in these ratings is visible. For the feedback type, we can summarize that there was also an interaction effect, as in one game, the absence of full visual feedback led to the fact that the performance of the player was not indicated properly anymore, which led to them losing the game a lot. When it comes to the comparison, that's probably one of the very important points here between the crowd and the lab. We conducted another lab study with 27 participants, 10 of them were female, in a similar and comparable age range of 20 to 33 years. And we could not find any statistically significant differences when comparing the conditions that we tested. This is also something we were working on at the ITUT. So we increased this work and extended the amount of games that we tested, and those tests also showed very similar results. If you are interested, you should have a look at the p.crowdg work item to follow this research. So to conclude this talk, we can state that with proper stimulus design and when we control the environment and participant behaviors properly, that it's possible to use the method of crowdsourcing to get a similar result compared to a lab study. This would also allow, as shown, the development of a questionnaire. The dropout rate were kind of high, but it's also in line with the dropout rates we see in speech quality assessment. The methods described at the ITU, recommendations P808 and P809, were really helpful references to come up with such a framework. Below, I listed you the key components of the framework again, and I would say that especially the engagement check and the integration of the degradations within the game was a really helpful step. This concludes my talk, and I thank you a lot for your attention, and I'm looking forward.
Thank you, Stephen, for this nice presentation. We have a few questions popping up, and I see one related to the fact whether these games and the framework itself are publicly available.
No, they are not yet publicly available. They are open source games. Partially we extended. There's a GitHub available where there was a basic development of them, but that was really basics in terms of mechanics of these games and the improvements and the inclusion in this framework. This is something we did not publish yet, but once we hone the code a bit and make it nicer, we plan to do it.
So a second question that was asked was related with the 95% confidence interval. So it was indicated here in the crowdsourcing that confidence interval was larger than in the lab. Can you elaborate on this aspect?
Yeah, the confidence interval, of course, depends largely on the number of data points you have there. I think they were not identical, so that might be one reason. If there are other reasons in terms of influencing factors caused due to this paradigm shift, I can't directly tell, but of course it might be possible.
Mm-hmm. And so another question related to the other effects that might be affecting actually the results. So gender and experience effects are mentioned here. Also content related is another aspect here, because you mentioned that you tested on a few games and where you indicated that there is absolutely no difference in terms of behavior. But the logical question then is, okay, how different were those games? Were they requiring a different type of interactivity, or was the interactivity actually at the same level?
Yeah.
So it would be interesting if you could give us some more information about those aspects.
Mm-hmm. So even though these games, they were, I would say, a bit abstract as we developed them, and they are web-based games where you also maybe have to consider certain processing powers and so on. We try to cover the basic mechanics of games, such as driving games and shooting games, so this point and click gestures and alike. So I think the games that we used, especially when we also include those that we use now for the work at the ITU, they should cover the major mechanics of most popular games. And in that aspect, I think it's also representable. It depends surely what you want to do with this research. For example, as I said, we used this one to develop a questionnaire. And this was absolutely sufficient to cause these degradations and use it for such an approach. And about the influencing factors such as user factors, I'm not sure if we analyzed that actually for this data set. I know that we did that for other data sets, also work at ITU that is very related to that, where we couldn't really find strong influence of these user factors, but those, especially the one, the gaming expertise, so how knowledgeable people are, frequently use systems and so on, that leads to the fact that they are more critical and rate and any types of quality aspects a bit more negative than people with less experience.
Did you account for the input devices that the gamers were using? Because this might be different.
Well, this is something we had to a bit trust on. So we clearly advertised them to all use a keyboard or a mouse, depending on what game was used. And I'm very sure actually that if someone would use, for example, a trackpad on a laptop, you would perform so bad that you wouldn't pass the engagement check. But yeah, other than that, we can't really find proof for this one. Yeah, for the displays, we at least had access to something like resolutions, and that's something you can track. But, for the specific hardware, that's I guess something you need to deal with when you do crowdsourcing studies.
I see.
That could be an influencing factor, sure.
Thank you, Mylene. Do you have further questions? No. Okay, so then I would like.
Yes,
sorry.
actually, there is. Sorry. Yeah, I was wondering. There is one question that popped up here because in your experiment, I understand that people are playing by themselves, right? Or did I misunderstood? So there is one question here I found interesting. So about what would you expect in comparison to a scenario where players play together and therefore there is some interaction? Would you, I don't know, maybe expect a worsening of your scenarios?
Yeah, I mean, these social aspects, this is something really difficult, even in lab studies, right? So typically we try to avoid that to have just more reliable results there. I think doing such a multi-user approach here would be more difficult because you would lose this benefit that you can have the degradation within the game. So that's tricky to do, actually. You can think of ways to extend that, maybe with some network controlling and simulations, but that's something we haven't done yet. But yeah, in general, social aspects in gaming are surely impactful, but we always try to keep that a bit out.
Okay, thank you. Thank you. Go back to you.
Thank you, Stephen. Let me thank you again for this nice presentation. And I would also like to take the opportunity for all the presenters in this session and the associated authors, of course, for their contributions. So this is also ending this session, and I believe we're going to move soon to the next session, but there will be a break in between. Bye all.
We come back at 3:10, right? Okay, thank you all, and see you around.
Hello, my name is Ronan Flynn from Athlone Institute of Technology, and I'm delighted to chair this virtual lobby session on day 3 of QoMEX 2020. In total, there will be 13 papers pitched by their authors at this session, 6 in lobby 1 and 7 in lobby 2. And both of these sessions will be running in parallel. There's an interesting selection of topics to be presented. They include sound localization in a virtuality task, a couple of papers on quality assessment, coding for real-time streaming, and actions in a virtual environment and the influence on subsequent behavior outside of that environment. For those attending the conference who want to observe and chat to the authors, you're invited to listen to the pitches from the authors and then decide which of the 2 hubs you want to enter to have further detailed discussion with the authors and questions and answers. For the authors themselves, you are asked to go immediately after your pitch to your own virtual Mozilla hub, where the question and answer session will take place. Participants are encouraged to visit all 13 individual hub rooms during the session. There is 1 room per paper, and each room can hold 25 people at a time. So if you find that the room is full, do try again at a later time in the session. So I hand you over now to the authors for their pitches.
Sorry, Connor.
Okay, so you're welcome. We're nearly there, coming towards the end of QoMEX 2020. So since we couldn't be here for the physical event in Athlone, I just added this little slide here showcasing the event where the physical conference would have happened and some of the other experiences that we planned for the social sessions, which was a boat trip on the River Shannon, a visit and the music session in the Ireland's oldest bar, which is called Sean's Bar. It's in the Guinness Book of Records, but I think we had a pretty good substitute for this last night. And I just want to say thanks to these businesses who, considering the situation, have been very understanding, and I want to wish them the best of luck in the future. And if you're ever visiting Ireland, we have the Sheraton Hotel, Viking Mike's boat trips, and Sean's Bar in Athlone. A final word of thanks to the organising committee. So you'll have seen this already, but it really was quite a significant team effort. You know, everybody chipped in at different times when the timeline required it, and I've learned a lot from many of you during this experience, and so thank you for this. So we had a separate execution team. So I think the session chairs for all the different keynotes, oral sessions, and hub sessions have done a fantastic job this week. So special thanks to them for the keynote, and in particular for the oral sessions. It's quite intense trying to coordinate everything. So well done to everybody on this. So next we have the hubs and lobby teams. So we had Pakia and Phoebe who were leading the efforts here, and they were the moderators in the various lobby sessions. And then we had another sub team who helped out configuring and setting up registering the speakers and presenters in the different rooms. So special thanks to all the team here, and best of luck with your own research, and particularly to Pakia and Phoebe who did huge work in the last few weeks getting the environments together. So finally, from the team point of view, nice work Tiago on the music. I think it went down really well, so thanks to him for that and all the effort on retuning me in particular. And last but by no means least, for anyone who's involved in any of the live Q&A or the keynote sessions, they'll be familiar with Connor. He did a fantastic job and did a huge amount of work, not just during the conference, but in advance as well. So for the final time, many thanks to our sponsors, the IEEE Signal Processing Society and the Qualinet Group, and our silver sponsors, our silver supporters rather, Bitmovin and two local companies here in Athlone, Ueda Technologies and Sidero. And finally, our diamond sponsors, Netflix, Deutsche Telekom, and YouTube. And thanks also to YouTube who sponsored the Best Paper Award and the Best Student Paper Award. So, where do we go from here?
Hello everyone, Tiago Falk here from Canada. Before I let Neil and Andrew pass the QoMEX torch on to us for next year, I would like to congratulate them on putting together this fine workshop. A first for all of us, a virtual workshop, and I believe you will all agree with me when I say that this was a true success. So congratulations, Neil, Andrew, and the entire organization committee. You've really set the bar up really high for us. So 2021, Dr. Amy Reben and I would like to invite you to come and present your work at QoMEX 2021 in Montreal, Canada from June 14th to 17th. The theme of the conference will be an immersive experience in a digital world, and it's going to have as topics conventional ones and classical ones, many that you've seen this week, for example, immersive QoE, gaming QoE, but we also hope to attract a number of special session topics that are relevant to what we are experiencing today with this COVID confinement, things such as user studies without users, how to conduct them, how to also conduct subjective testing in this COVID-19 era, and so on. As of today, we're moving forward with a organization of an in-person event. So we have the convention center at the École de Technologie Supérieure booked. They are awaiting us with open arms. They are strategically located in downtown Montreal, near the Old Port, near the St. Lawrence River. As you can see here on the screen, there's a wide range of accommodations at a wide range of prices to accommodate all tastes. We have a number of social events. We have nice food planned for 2021, but we also have a number of events that will spotlight early career researchers as well as celebrate diversity and inclusion. We saw that this was something that was very successful this year, and we would like to continue with that in 2021. Knowing that June is a time of vacation for many of you, I leave here on the slide a number of events that are happening around QoMEX 2021. So just a week before, ICASP will be hosted in Toronto, which is a 5-hour train ride from Montreal. To those of you that are Formula One fans, it is predicted that the Grand Prix de Montréal will happen between June 11th and 13th, so just before QoMEX. And if you are a jazz fan, the world's largest jazz festival that happens in Montreal every year is planned to be happening at the end of June. So if you're coming with your family, there are a number of events that you can take advantage of. I don't want to take up too much more of your time, so I will leave here on the screen the website of the QoMEX 2021 conference. It is already up and running and live, and there you will find the call for papers. Do expect to receive an email from us within the next couple of weeks with a copy of this call for papers. And before I leave you, I just wanted to show you a few important dates to remember. So special session proposals, early December, full paper submission by mid-February, short paper submission by mid-April, and we look forward to seeing your submissions, and I look forward to seeing you in Montreal next summer. Thank you everyone, and I wish you all a wonderful remainder of this week. Bye.
As we've reached the end of QoMEX 2020 and all the papers have been presented, it's now our pleasure to get to the best part of the conference where we award the Best Paper Awards. As is the tradition with QoMEX, there will be 2 awards, a Best Paper and a Best Student Paper. It should be noted that the Best Paper can also be won by a student. The awards committee was chaired by the awards chairs, Christian Timmerer and Alioja Smolich, and it also included the TPC committee of Mylena Faris, Anil Kokaram, and Alexander Raka. The assessment was a multi-stage process. An initial shortlist from all submissions was made based on the peer reviews. The papers and the videos were then reviewed by the committee, and the awards chairs selected the best student paper, and the TPC chairs selected the best papers from the shortlist. Now to go to the awards themselves. The awards this year are sponsored by YouTube, and the best student paper is entitled PCQM, a full reference quality metric for colored 3D point clouds. And the authors are Gabrielle Maynet, Yana Neme, Julie Digui, and Guillaume Lavoie. And so I'm delighted to announce the winners of the best student paper, Gabriel and Yana. Congratulations.
Thank you.
Thank you very much.
Thank you so much.
And now for the Best Paper Award. So the process for Best Paper Award was incredibly competitive. There were a number of very close candidates. And we have a new emerging topics for the QE research game to seem to gain traction each year. And this year, the point cloud was particularly popular. So the winners of the Best Paper Award sponsored by YouTube for QoMEX 2020 are Jerome, Maria, Christian Timmer, Ali, Philip, and Raymond. And the title of their paper is Objective and Subjective QE Evaluation for Adaptive Point Cloud Streaming. Congratulations, guys.
Thank you.
Yeah. Okay, so congratulations to the 2 winners for the best paper and best student paper. And so this is pretty much it from me. I'd just like to thank everybody who submitted and the team here, and I hope you keep all safe and well, and I hope to see you all in Montreal next year.
Yeah, I'd like to add my thanks along with Niall. I think he's thanked everyone who's worked behind the scenes. There's been a lot of tireless work done to keep this conference online. It certainly wasn't what we expected when we signed up to it, but I think it's passed off fairly well. So I think everybody did enjoy it. Thanks to all the attendees. I think it must be a record. There's 114 people watching now, and for a closing ceremony of any size of conference, I think that's pretty impressive. So thank you all for sticking around for the end. I'd just like to add to the thanks that Niall made. I'd like to thank the reviewers for all the peer reviews and for getting them in, and especially the TPC chairs for all the hard work they put.
Say that again.
Yeah,
he knows. Yeah.
For all the hard work that they did putting together a very interesting technical program. I think everybody really enjoyed all the different papers that were presented, and there was really good interaction in the virtual hubs and on the sessions, on the oral sessions. I'd also like to thank all of the session chairs. I think it was a novelty for them as well, having to chair things on a live video stream rather than sitting up at the front of a conference venue. So before we go, I have two small requests for you. The first is everyone before the conference got a pre-conference questionnaire. So I'm going to invite you to, before it's too late, complete the post-conference questionnaire. We hope to capture a lot of useful learning regarding running a virtual conference and trying to maximize the QoE of conferences so that other people, not ourselves, but other people who decide to run virtual conferences again in the future. I'm not sure it'll be Niall and me after being thrown at the deep end, but I think there's a lot of learning can be taken out of our experiences to maximize the QoE for attendees and presenters in the future. So that's my first request. I'm going to send around the email on Slack, on the Slack channel now, and I'm also going to send it to you via email. But if you could fill it in the next couple of days while the memories are still fresh in your minds. The second request is that I'd like to invite everyone back onto the Zoom social channel, and if you're still there, then we'll try and take a group selfie, and there'll also be the opportunity for a bit of a post-conference chat. So without anything else, I'd like to say thank you very much, thanks, and goodbye from QoMEX 2020, coming to you live from Ireland, and so long and goodbye until next year in 2021 when we'll go visit Tiago in Montreal. Thank you.